The universe is marvelous. Just look at the sky. Huge planets, bright stars, vast galaxies, massive clusters. It just fills us with tremendous amazement. In the last century, our exploration of the cosmos has reached unprecedented depths. From the first echoes of the Big Bang to the accelerating expansion of space, from dark matter and dark energy to ripples in space-time itself. Yet, with every answer, deeper questions have arisen. How far are we in understanding our universe? What lies at its beginning? Are there limits to knowledge, observation, and even comprehension? Is the astonishing order of the cosmos merely accidental? Or does its beauty, fine-tuning, and mathematical elegance point toward a deeper intelligence and purpose, as some of the greatest scientific minds have reflected across generations? To explore these profound questions, Bhaktivedanta Institute invites you to an extraordinary voyage through our cosmos, where some of the world's most brilliant scientific minds will share their insights and discoveries, including Andre D. Linde from Stanford University, John H. Schwartz, theoretical physicist, Caltech, USA, Wendy L. Friedman from the University of Chicago, Ofer Lahav from University College London, Avi Loeb, Harvard University, USA, Pankaj S. Joshi International Center for Space and Cosmology, India, and many more leading thinkers from across the globe. This is a space for rigorous science, open inquiry, and meaningful dialogue, where curiosity meets humility. Welcome back to your own astonishing home, the universe.
Okay, so we shall start now. Across time zones, disciplines, and traditions of thought, we gather for a single shared pursuit to understand a universe that continues to exceed our understanding. Good evening, good morning, and good afternoon to our participants joining from across continents, distinguished speakers, respected scholars, colleagues, and students. My name is Siddharth Tiwari. I am privileged to be your host for today's program. A warm welcome to day 3 of the Golden Jubilee Lecture Series, Voyage through the Cosmos, History, Models, Theories, and Fundamental Issues in Exploring the Universe. Across time zones and disciplines, we gather today not merely to exchange ideas, but to engage with questions that have resisted closure across centuries. If the first 2 days brought us to the edge of our current cosmological frameworks, today invites us to examine something more fundamental. Not just what we know about the universe, but how stable that knowledge really is. From the evolving nature of dark energy to alternative cosmological paradigms to the questions of whether a big picture is even attainable. Today's sessions move from models to meta questions about models themselves. Let us begin. The timing of the lectures will be 5 p.m. to 8 p.m. from Monday to Friday and 10 a.m. to 1 p.m. on Saturday and Sunday in Indian Standard Time. Before we move to today's lecture, I will briefly go through today's schedule. The first talk will be delivered by Professor Ofer Lahav from the Department of Physics and Astronomy, University College London, UK. He will speak on fascinating topic, is dark energy evolving with cosmic time? The second talk will be delivered by Professor Tim Eastman, formerly of the University of Alaska, USA. He will be speaking on the intriguing topic, plasma cosmology. The third talk will be delivered by Professor George Ellis from the Mathematics Department, University of Cape Town. He will speak on the nature of the universe, the big picture. Before we proceed further, I'd like to request all participants to please scan the QR code displayed on the screen to submit your questions to the speakers anytime during or after the lecture. You may take a screenshot or a photo of the QR code. Alternatively, the Google Form link has been shared in the chat box. It is my great pleasure to begin with Professor Lahav. Professor Lahav is the person chair of astronomy at University College, London, and leading researcher in the study of the dark sector of the universe. As a co-founder of the Dark Energy Survey, DES, and long-serving chair of the Science Committee, Professor Lahav coordinated the efforts of hundreds of scientists mapping hundreds of millions of galaxies, producing one of the most comprehensive probes of cosmic acceleration and the distribution of dark matter. His work focuses on characterizing the properties of dark energy and testing whether it arises from a cosmological constant or from modifications to Einstein's theory of general relativity. A pioneer at the interface of astrophysics and data science, Professor Lahav introduces advanced machine learning and artificial intelligence techniques into cosmological data analysis, including early applications of neural networks in the early 90s for galaxy classifications and photometric redshift estimation. By combining massive observational surveys with sophisticated statistical methods, his research aims to shed light on 95% of the universe remains invisible. Today's question is deceptively simple. Is dark energy evolving with cosmic time, but embedded within it is a deeper inquiry? Are we observing a constant or witnessing a paradigm in transition? Professor Lahav, we are honored by your presence. The platform is yours now. Thank you.
Thank you very much for the very kind introduction. I hope you can hear me well.
Yes.
It's a pleasure to participate in this very exciting program. And I understand that over the past 2 years, two days, you've heard very nice talks introducing many of the topics. And today I'll zoom in on one ingredient of the universe, a mysterious one, dark energy. So if that's okay, I'll share the screen now.
Sure, sir.
Can you see it well?
Yes.
Okay, very good. So just as a quick introduction, I should mention that, yes, I'm based at University College London. Previously, I spent nearly 20 years in Cambridge. And I'm also a member of a number of big collaborations, in particular the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI. In fact, you can see if you can see the arrow, can you see the arrow when I point? Yeah. This is the DESI catalog or map. Each dot is a galaxy. There are now 46 million galaxies which measure spectra. On the right-hand side is a map produced from the Dark Energy Survey. And this is actually this region you see here. Can you see my arrow, by the way?
Yes, yes, sir.
Yes,
We
okay.
can see.
Yeah,
Yeah.
okay. So this region is actually encompasses a map of the dark matter. So you may puzzle, if it's dark, how could I show it? It is a reconstructed map using weak gravitational lensing. We'll come to it later. Just for orientation, you can see there the Milky Way from the Gaia satellite and the Magellanic Cloud, is large and small. And of course, almost everything we do is within a paradigm or framework that was introduced by Albert Einstein, and will be more specific about what he said about dark energy. And in any case, we see him here experimenting gravity. I don't know if at the end, if he survived being on the bike or not. Okay, so moving to the next slide, I'm going to go through a brief history of cosmological constant and cold dark matter. I know that especially this forum, your university, has a lot of interest in philosophical and historical elements. So I'll do my best as a humble astronomer to comment on that. I mentioned I'll mainly show results from two projects which are, in a very mature stage. In fact, most of the results already published, but I'll also talk about the future. And the question is really, as was also introduced by the session chair, is dark energy just a constant with time? And by that I mean the density energy of the density of the dark energy, which means it's just Einstein's cosmological constant, or is it evolving? And of course, the question is, what's next? Okay, what are the expectations? Can we pin it down better? So this is very much of an open question. I would like you to appreciate that point. I'll allow myself to slightly deviate from the standard physics type of talk and talk a bit about the social value of studying such elusive topics as dark energy. And also I'll comment on AI, how it can serve us in cosmology, but also maybe to say that cosmology is helping in AI because we have all these big data sets and big questions. So most of you probably are familiar with the concept that there was a Big Bang 13.8 giga years ago, 13.8 billion years ago. And since then, the universe is expanding. There was a period, a very brief period called inflation at the beginning. And then the universe carried on expanding. And about 25 years ago, there were measurements that suggested that the universe at present is accelerating. And this is pretty much still the picture. If you look at the central kind of cake, this is what the different slices are, the budget of the universe, only 5% are ordinary matter, and now we think 25% is dark matter, cold dark matter, and 70% dark energy. I have to emphasize two things. One is, this is the composition of the present epoch, okay? In earlier times, the universe was denser, so dark matter was more important. Also, I have to say that this picture is not perfect, as we'll discuss. There are some tensions. So will these tensions disappear? These tensions, that means disagreement, will it disappear, or would it persist and lead to a new paradigm? I have to say there are probably people at different academic age in the audience. I say, when I did my PhD in Cambridge in the late 80s, the story was quite different. Everybody talked about the standard model where there were 5% baryons and 95% cold dark matter. So at that time, the dark energy was believed to be zero. It was not known as dark energy, it was cosmological constant. And if you would talk about cosmological constant in a lecture, people would probably laugh at you. And then I was fortunate enough, in the early 90s already there were some issues, and myself, I wrote a paper in 91, but then it was really 98, 99 when the two supernova teams showed us that indeed there is something which causes the acceleration, and it's probably that type of something, dark energy, or maybe is a bigger name, a wider concept, which includes the cosmological constant. Cosmological constant, of course, goes back to Einstein. I recommend reading this paper. It's in German, but you can find the English translation on the website of Princeton University. And it's really in 1917 that he put this paper he introduced lambda for a number of reasons, not just one, but one of them, he didn't like the idea of expanding or contracting universe, so he introduced lambda, as we'll see in the next slide. So this is Einstein's equation in full glory. In fact, on the poster of your conference, I saw the same equation, and I was quite, in a way, interested to see that you also put lambda, so this is the cosmological constant, on the left-hand side. These R you see there, they describe the curvature, and Einstein himself in 1917 put it on the left-hand side. On the right-hand side is what's called the energy momentum tensor, which means you put something there, it would affect the curvature. That's what John Wheeler told us, that matter and energy tell space how to curve, and then space tells matter how to move. So it's interesting. I want to emphasize that point, that Einstein put it on the left-hand side, you put it on your poster left-hand side, which I interpret as kind of another constant of nature, a bit like big G or C, right? But in fact, most of our colleagues, especially in particle physics, would like to put lambda on the right-hand side and absorb it into T mu nu, and then it has a meaning of energy, and that's why the name dark energy. But to be honest, we still don't know if it's on the left-hand side or right-hand side. It's also another interesting exercise is to take that equation, which is very complicated, and take the limit of weak field. And what you get then is a very nice equation, and most of us know it from our childhood, from school, that acceleration is minus gm over r squared. So that's the force that got the apple to fall on Newton's head. But you have a residual here, which is this lambda over 3 times distance. And if lambda is positive, it's a repulsive force. So in that interpretation, you have the acceleration, things are bringing you together, and you have the lambda force pushing. You may ask me, or students like to ask, can we see it, in day-to-day life? No, this term is very, very small. So when we take airplanes, whoever designed the airplane and the motion of the airplane doesn't care about that. Planets in the solar system, again, not really important. However, and I was surprised when I saw it, we did a paper with a student some years ago, when you look at Andromeda and the Milky Way, when they fall towards each other, this force is actually there. It's repulsive, and it changes some of the dynamics of the system. So on scales of megaparsecs, millions of parsecs or millions of light years, this is actually important. There's another interesting point, which is little known, that actually Newton in Principia suggested a linear force. He didn't call the constant lambda, but he suggested that, and he even said that it was very remarkable. And you can read what he said, or we also you can find on my website a popular article which explains why he suggested 2 forces. Einstein himself decided that that's not true. What he put in, because a few years after he suggested 1917, Hubble and Lemaitre discovered the expansion of the universe, and Einstein felt very upset about it, that he basically put a constant which was not needed. On the other hand, his friend Arthur Eddington, and here they're seen sitting together when Einstein visited Eddington in Cambridge. Eddington actually liked it. So I think this is the original paper, 1917, I mentioned, and you can find it on the Princeton website. And you can think of it as some modification, really. But the key point is that Einstein, he added a constant, but you have a constant that could have any value. He chose a value which is 1 over the size of the universe squared, and this gave him a static universe, which is neither expanding nor contracting. But he somewhat overlooked and of course we should respect Einstein, but it's somewhat overlooked that this lambda could be any value. So you can have a value which gives you a static universe, but you can also have a value which gives you an expanding universe or contracting universe, okay? In any case, it's quite remarkable, this paper he wrote, 1917, is what is driving now the work of hundreds, if not thousands, of scientists in projects which cost billions of dollars. So I think it's all very exciting. We're in an exciting time. And there's this question about left or right hand side. And I mentioned the missed opportunities. He could have said that it's, it could have a different value, which would give acceleration. But the other point which you overlooked, which other physicists at the time showed, that static universe is unstable. So it wouldn't have worked. Anyway, so I hope you get the idea. People ask, was Einstein right or wrong? So he was right in introducing this constant, and the data more or less agree with that there is such a thing, but he was wrong on picking up the wrong value for that. This would be my short summary. Now, for those of you who want to see a bit of equations and formulation, you probably remember that any substance in nature could be characterized by an equation of state, and it has pressure and density, and the ratio, if you put the speed of light squared there for units, is called W. And for example, if I just look at just matter, W would be 0. But if it's, for example, radiation, it's a third. Now, we can do a textbook exercise and ask, if I tell you that's an equation of state, what is the density? How does the density change if this W is a constant? And you have that equation. So if W is 0, the density drops like the cube, 1 over the cube of the scale factor of the universe. It's kind of intuitive. If it's a third, it's a to the minus 4, which is a bit maybe less intuitive, but you can explain it in other ways. If it's, so you can make plots of this density, yeah? This is at earlier times. This is the present. So the present, we have 30% matter, that's dark matter plus baryonic matter, and we have 70%, that's the blue point. But in the past, the matter was much denser. But if Einstein is right, then you can ask, for what value of W would that rho be a constant? And it's easy, right? It's -1. So dark energy is a strange, or cosmological constant is a very funny property that it's actually negative. Now, the question, what is it? So when it's exactly -1, it's lambda. If you force it to be a constant, measurements show that it's about -1 to 2%. But if you allow it to vary with time, you find that it's more comfortable deviating from that value. And that's the title of my talk, right? Is it the case? And that's the title of the rest of the lecture. So I told you there is some signs of that lambda. Einstein talked about 1917. Occasionally it appeared. You can see literature from the 50s, from the 60s of last century. It comes and goes. I remember one calling me when I was very excited as a young man. He said, "Don't worry, every cosmologist is going through a lambda phase." But it seemed to persist, and there are these very important papers by Jim Peebles, won Nobel Prize, Weinberg won Nobel Prize, not for that, but they are well-known physicists. And that's while I was in Cambridge, one of my mentors there, Statio, did some work. He did not measure directly omega matter. He measured omega matter, but he did not measure omega lambda, sorry. He measured omega matter, but he found omega matter to be about 0.2, and he did 1 minus 0.2 equals 0.8. So he said, must be a lambda of 0.7, 0.8. Now we would say 0.7. And me as a young, naive student, I did a little paper in 91, together with Lilie, Primack, and Rees, where we also looked at different possibilities of omega against lambda. And we concluded that, we can actually not rule out the possibility that lambda is non-zero. Now, what happened then is that a group of two teams looked at supernova exploding stars. Actually, they're made of a binary, and one star accretes matter from the other, and then there's an explosion. And this has to do with Chandrasekhar's mass, which I'm sure most of you are familiar with, which was defined by the famous Indian astrophysicist Chandrasekhar, 1.4 solar masses. So this is believed to be the mechanism. In any case, nature has been very kind and produced for us standard candles. So if we believe that the same mechanism is behind every object called supernova, and we do some corrections, we can then learn about it. And that's what happened in the late 90s. Two supernova teams could not explain the data unless they put something like a cosmological constant. You can do the same thing with standard rulers. So nature is kind enough to give us some features in the distribution of galaxies, which we call baryonic acoustic oscillations. They also appear in the CMB, and therefore you could basically measure that. So it's geometry. It's geometry. But you can also count the number of clusters in a volume, which would be different if there is a cosmological constant or not. And you can do this technique, which is very beautiful, called weak lensing, that objects in the distance, their shape gets distorted. So maybe if this was almost a circle, by the time we see it, it will have this very narrow shape. And we can look at these distorted images and look at how they're correlated over the sky and learn also about dark energy. So these have been the four primary techniques to learn about the dark energy. And this, of course, has led to all these activities after the supernova discoveries of this telescope. And this is a big array of CCDs on the telescope in Chile. So this is a project I spent nearly 20 years on with many, many other colleagues, about 400 led by Fermilab in the US. And this is a 4-meter telescope where the camera was upgraded, and part of it was built in our basement at UCL for both DES and the other project DESI. That's on a telescope in Arizona, and DESI is actually just about to finish the original plan in a few days, sometime at some point, very, very soon. So there will be probably a press release about that. And that's about, DES collected about 300 million images. DESI collected about 46 million spectra. But this is just the here and now. Rubin on the neighboring hill is a brand new telescope and already collecting data. And so is Euclid, a space mission of the European Space Agency, also collecting data. So those two is a big jump relative to this, but that's how science works. When I was a student, we had thousands of galaxies. Now we're talking about billions. So this is just a summary of some of them. You can see the amount of data. You can see the number of galaxies. I mentioned it will go towards billions. You can see the cost going from 100 million to a billion. And I like to tell our funders that putting $1 billion is a good deal, because each image of a galaxy is only $1. I don't know if they buy this argument, but we try. And also you can see the number of scientists goes from hundreds to thousands. So it's a different type of doing science, a bit like particle physics now. I mentioned already these two telescopes in Chile and Arizona. I can only say I was there for a week in 2015, and there was a huge earthquake, 8.3, but it survived. Telescope survived. So shows you how strong it is. It's led by American laboratories, Fermilab and Berkeley, and as I said, UCL bought the optical correctors, and these are the numbers of objects achieved. This is the camera. It's the same camera, same principles as your mobile phone, but it's weighs several tons. And for those interested, especially also in the history how it happened, we produced this book written by the people who created Dark Energy Survey, and it even includes at the end chapters on philosophy and anthropology, etc. Dark Energy Survey not only looked at the static universe, it also looked at supernovae, and the Nobel Prize to these teams that discovered the leads of these teams, Perlmutter, Schmidt, and Rees, they use 42 supernovae, got Nobel Prize. Now DES can measure 1500. And you see the light curve, you look at the galaxy, it looks very boring, and suddenly there's an explosion, and this is the amount of light and the decline, and you use the peak luminosity with some corrections to use them as standard candles. So this is a visual impression of all 1500. And then you plot what's called the distance modulus against redshift, and you get this diagram, the Hubble diagram. There is data from DES, and that's from nearby stuff. And if it was a perfect cosmological constant, should have been just a straight line, but you can see, for example, the green line shows some deviations from that. Baronic acoustic oscillation, similar story. Its nature is kind enough to produce features which have to do with the competition between the plasma and the dark matter, and it leaves behind some features which you can imagine them as rings, but when we use power spectrum analysis, it's the Fourier, or you do here's the correlation function. It's the probability of finding a galaxy at a particular distance s from another galaxy. And you see this subtle, it looks a bit amplified here, but it's a very small feature that you see. And it's this feature, which is something like, in some other parameterization, it's of over 150 megaparsecs, that you use as your standard ruler, right? Just the same way you use the standard candles. So these are the techniques. The same thing happens with the CMB, and you can see results from Planck in orange, but also from another project called ACT. And you see, look, it looks like a textbook, picture of these fluctuations against the distance. And so what is the problem, right? So the point is, this is the key, maybe you can think of this as the key slide of this talk. And I'm conscious of the time. I'll try to finish on time in about 15 minutes, if that's okay. What the key point here is that if we so as I told you, when I was a student, late 80s, there was no lambda. Then the supernova people told us you need lambda. Now, if you fit separately the baronic acoustic oscillations from DESI, and separately the supernova from DES, and separately the CMB from Planck or ACT or Space or SPT, another project, South Pole Telescope, each of those three fits the data all right. Okay? The problem is when you try to fit them all together, they fit each of them okay, but it gives omega matter, the thing which is supposed to be about 30%, you see, one gives something like 0.25, one gives something like 0.35. So for the same model, they get slightly different fits. So you know it even from first year laboratory, right? You have three parameters. Do they make sense? The problem is when you put all these three together, the supernova and the CMB and the acoustic peaks in the galaxies, they're unhappy. Okay, so the tension and the need to move to this kind of evolving universe, evolving dark energy universe, is because it's when you have all three of them together, that's what you get. If you say, I don't believe two of them, I only want one of them, you could be happy. You could say it's lambda CDM with omega m of 0.32 or something, and you just be happy. But it's when you're trying to take a more holistic view of using three techniques that it's difficult to fit them all together. So this generated a lot of interest. In fact, exactly a year ago, on the 19th of March, DESI published that, and many authors, I'm one of them out of many, and this generated a lot of excitement because there is this tantalizing evidence for evolving dark energy. And you can see it got a lot of attention in the Guardian newspaper and the BBC. Experiment challenges Einstein theory, and so on and so forth. So you can now, it's a bit like going to court. You can have one lawyer saying it's just lambda, W is -1, and you can have another lawyer saying, no, it's changing, right? So I'll try to do both. In fact, I'm doing some work on that with colleagues, trying to look at the different options. So the thing is, when you have just W, you force it to be W, you get something which is consistent with -1. But you have to be a bit careful that you force it to be a constant W. DESI, you can see if you do this equation of state, I told you when it's -1 exactly, it's lambda. So probably you look at it and you tell me, look, it's not exactly what's going on. It's actually not, it's actually going down. And I say yes, but the best data point is there, and it's only 2 sigma away. And also there's some subtleties that the CMB dominates it, so it forces it to be close to -1. But if you do it non-parametrically, you can see there's a tendency of this W to change with time. And that's exactly the next. So this is the second lawyer is saying, I would like to have evolving dark energy. So this is the plot I just showed you, how the density changes with time. And it's really weird because this is earlier times. So the universe, if this measurement is correct, gets this density and it goes up and reaches a peak and then declines. And in terms of this region, is actually called the universe a phantom attractive because it expands. You'd think something expanding it will have less, smaller density with time, but this does the opposite. And this is another, those of you who like frequency statistics rather than Bayesian, this is in terms of how many sigma. And this is, by the way, parameterization of this time variation. It's two parameters, W0, WA, and A is a scale factor. So at present, A is 1, so it's just W0. Yeah? I hope you're with me. So the point is, for different combinations of data, you would have, if you're a believer, if you're the lawyer who likes lambda CDM, you'd have liked all the data to be there, but it seems that the data prefer to be further away by something with 3 to 4 sigma. I would say after some recent work, people think it's more like 3 sigma. And then it's your judgment as a physicist. Do you lose sleep at night over 3 sigma? You say there's a problem and maybe there's a new theory. Or you say, well, 3 sigma, there are always problems with the data. It might go away. So this is a very important plot and the main message of this talk, that we don't know for sure, but there's this tantalizing evidence or tentative evidence, intriguing evidence of evolving dark energy. So there are ways of rescuing. If you are the lawyer who likes lambda CDM, you will come up with all kinds of explanations. Data were corrected, improved, and then it brought the supernova results from 4.2 sigma to 3.2 sigma. Other people are very worried. This is a group from South Korea. They're very worried about the properties of the galaxies, of the host galaxy. How does it correlate with the luminosity? The cosmic macro background, there are details about the statistics, but also there's a constant called, not a constant, a parameter called tau. That's the optical depth to reionization, and depends what you put there in the CMB, things can move around. So if you put a higher one, it helps again with lambda CDM. And some people even are prepared to sacrifice the curvature of the universe, which we like to believe is 0 for that. So I made a very simple plot here. It's a bit crowded, but I just want to show you with all these options. No, the scale factor, it's only when it's lambda that it goes. I plotted it. I'm being a bit usually you see plots ending at present, which is here. This is the beginning, 0, and that's after 13.8. Here I plot it all the way to 17 gigayears. So I look into the future, and I'm basically saying the universe will expand forever in all these cases, all these measurements, even if it's not just lambda, but other values which are consistent with the data. But it's only in lambda that you'll see this amazing exponential growth with time. And you can look at other parameters there. And this is just zooming in because people ask, okay, with these new results that's evolving in time, will the universe collapse? Will it have a big crunch like in this toy model? Okay, this toy model, the dotted line is not a measurement. You start somewhere and it expands and then collapses again, which could be, it's not in contradiction to Einstein's theory, but it looks like even if you like lambda, as I said, it's an exponential growth. If you like this W0, WA with the measurements of Des and Desi and so on, it's not as dramatic, but it will still expand forever. So I'm sorry to disappoint those of you who like big crunch. I myself would have liked to have a big crunch, but nature maybe wants something else. And I'm doing this work with a colleague, Paul Shah. We'll publish it hopefully soon. So I'm getting there. So what is this dark energy? Is it just we're making some mistakes with the data? Is it just lambda? Does it change with time? I haven't told you, those of you who are particle physicists know that in particle physics, if you calculate, it should be the energy of the vacuum. How come vacuum has energy? Because, even harmonic oscillator has an energy in quantum mechanics, the ground state. If you add all these modes, you get a huge value of dark energy, much more than what we measure. So what's going on here? And is this a signature of modified gravity, maybe? Maybe it's an inhomogeneous universe. We can also move to the more esoteric work, and I think there are talks at your conference about multiverse and the anthropic principle. The universe would not be the way it is unless we were here to observe it. Many possibilities. There's always the unknown unknown. Maybe someone will give you a talk 10 years from now and will tell a completely different story. So I listed here a few open questions. Is it on the left-hand side, as in Einstein paper and on the post of a conference, or is the right-hand side? Could it be W less than -1, phantom, as some measurements suggest? And could it change, with W? When do we decide we know the answer and we stop? How do we live with this discrepancy of 120 orders of magnitude? But maybe there's a room for a new theory, and some people speculate maybe this lambda, which is just one parameter, maybe it hides, maybe behind it, there's lots of kind of unknown physics, and maybe that's also the link between general relativity and quantum mechanics, right? Maybe that's also, and maybe, who knows, maybe thermodynamics or some other branch of physics which we don't even know exists yet. And maybe it will take another 100 years. Lambda has been around for over 100 years. Maybe we need another 100 years to figure it out. I know, it depends. There's also the question, which I'm sure is true in every country, and there recently have been some budget cuts on this kind of curiosity-driven science. And I wrote an article with an economist in Oxford, an economic historian called Avner Ofer, and it's in the Royal Astronomical Society journal, Astronomy and Geophysics, of February. We wrote it a long time ago, but it appeared in the month that there were just cuts in the budget in the UK for astronomy and particle physics, so it's funny timing. In any case, we're trying to explain why it's so important for the society to have even this esoteric topic. It's because we humans, we are curious. We want to understand where we live. But as you also know, there's lots of benefits to it in terms of developing technology, telescopes, and eye, and so on. And the landscape is very promising. This is the number, depends which plot you want. But if I focus, I look, say, this one, which is against year, you'll see there's almost like Moore's law that we make projects bigger and bigger. So this is the time, more or less, I did my PhD, and look where we are now. And those of you young and energetic, you're very lucky, but you'll have to probably work harder than us to analyze so many millions and tens of millions, hundreds of millions, even billions of galaxies. So, it is a golden page, a golden age for the subject.
Just a
Hello?
Hello. Sir, just a gentle time check, about 5 minutes left.
Yes. Oh, so I have another 5? Okay, I'll finish in a few minutes here. Thank you. So, we have to really appreciate that time, but we may not have so much money in the future, We're already doing projects for $1 billion. Are we going to get project for $10 billion? I don't know. So then also one cannot give a talk these days without talking about AI. I was very lucky to work on it already in the early 90s to classify galaxies and then to do photometric redshift. So I just want to mention that. And also that, there's a lot of room, and I was very pleased to see the program of your conference that, there's a lot of room thinking. What does it all mean? Because it's one thing just to have another number. What does it all mean? And, when do you decide you put a new entity, like people hypothesize Neptune and it was found, but people also hypothesize Vulcan and it was not found, right? So we don't quite know. And there's a question, when do you stop? When do you think you know the answer? But you never know, because I thought that we know that it's just a cosmological constant until about a year ago, and now it looks maybe it's not. So I think you have to decide about it. So these are some thoughts with Joe Silk we had some years ago. And finally, because I mentioned the AI, and I know there are many young people in the audience, at UCL we started 9 years ago a program where the students are prepared to do a PhD in astronomy or particle physics, but also in machine learning. So they come out of the program with 2 qualifications, and some of them stay in academia, some of them go to industry, and actually part of the 4 years they spend 6 months in industry of AI. It could be a private company, or it could be a government department. For example, a student of mine went to the Treasury, another one went to do some analysis of fraud detection, right? So I think we'll see this happy connection between AI and cosmology, and I think we learn a lot from computer scientists, but maybe they can also use our data, which is public. It's not as complicated as data for health, and could be cross fertilization there. So this is actually my last slide, and my summary, based on current observations. This may change, of course. Based on current observations, Einstein was right that lambda exists, but he was wrong about its value. So the value we like today is something which gives acceleration, not gives static universe. Standard lambda CDM survived, 30 years, for 30 years almost. It's a big achievement, for a theory to survive so long. But it could be that dark energy evolving with time. And if it's true, then it's going to be paradigm shift. Okay, this will be a shakeup for physics. And it's definitely important to test lambda cold dark matter model further, and that's why we're having on the horizon Euclid and LSST, and it's going to be, really a golden age for cosmology. So this brings me to an end. Thank you very much for listening.
Thank you, sir. Thank you for this rigorous and deep talk.
Shall I stop sharing now?
Yeah.
Yeah, okay, right.
So may I now request the team to share the question. So now this is time to take some questions and answers. And a gentle reminder to the audience, you may continue submitting your questions by scanning the QR code displayed on the screen. Also, the Google form link has been shared in the chat box that can be used. So now this floor is open for a brief discussion. So the first question what I received from Kumar Ravi from Swami Vivekananda University, West Bengal. It seems that the need for dark energy arises specifically when we interpret cosmic acceleration within general relativity as in the lambda CDM model and its extensions where a negative pressure component is introduced by hand. In contrast, in modified gravity frameworks for intense FR gravity, the acceleration can emerge from the gravitational dynamics itself without invoking a separate dark energy component. So, is it fair to regard dark energy as a framework dependent construct rather than a physically established entity?
Yeah, thank you, Kumar, for this question. I think you touch on a fundamental issue here. So I would say there are different schools of thought here. You can see, you probably, from the question, I can see you're very familiar with the literature. So, one can really stick to some sort of dark energy family of models from the beginning and their scalar fields, things like that. Or one can do the kind of more curvature type f of r. There's a third school of thought which is more phenomenological, that you don't impose a model, and in a way this W0 WA is agnostic, right? It just says something changed with time. And yes, you're right, you're still using GR for that, but it's within that. And then once you have W0 WA, like those I showed, what do you do with it, right? You have to assign some physics to it. So that's my take on this. I think it's good to have all these approaches, ab initio approaches, and to maybe try f of r and to see where the difference is. I should say that I mainly focus with the oscillations, baronic acoustic oscillations, and with the standard candles, supernova, on the overall expansion of the universe. But it's also important to look at the evolution of clustering, because it would also be different if you have f of r or dark energy. So I think there's a lot still to do there. Thank you.
So shall we move to the next question? Okay, so Dev Dutt from Himachal Pradesh University Shimla. Can we detect dark energy with help of gravitational waves? Is there any experimental evidence regarding dark energy which is detected by gravitational waves?
Yeah, so that's obviously another exciting area, gravitational waves, which was also predicted by Einstein, and as you know, a lot of work has gone into building instruments and so on, and the first detection was in I believe 2015, so it's over 10 years ago. Many experiments are going on, including in India. So already, if you remember, just from the one of the first detections, there's already a very serious constraint on what is the speed at which gravitational waves propagate. Okay, and there's this very strong limit that it's essentially like the speed of light. So this was very quickly, because there was the propagation of the gravitational waves, and there was also a signal coming 2 seconds after that. And from that, one can derive that speed of gravitational waves, same as speed of light. It turns out that this by itself rules out many models as alternatives to gravity. At the same time, there are also people now thinking about, I just heard some discussion yesterday, people looking at all kinds of techniques, for example, pulsar arrays, which could also constrain differences in dark energy. So I think we're not quite there yet, that there are strong numbers, but we can certainly use gravitational waves for that. And last but not least, but the binary neutron star at the time, if you remember, because we could tell also the distance of that, and the redshift was also used to get the Hubble constant. So indirectly, it's not directly dark energy, but it helps to pin down the Hubble constant. There's only one object so far, as a bright siren, as it's called, but there are many other dark sirens where you don't actually know you cannot exactly localize it. So altogether, this is not a test of cosmology through the Hubble constant. But yes, I think we should certainly flag that. Yeah. Yeah.
Okay, so moving to the next question. It is from Dr. Bharat Pandey, Government PG College, Uttarakhand, India. Sir, I want to ask, Einstein introduced the cosmological constant as a fixed term, but could dark energy instead be evolving with cosmic time, indicating physics beyond Einstein's original idea?
Yes, so what I was trying to show you, that if we look at the data, and if the result is W equals -1, it's Einstein's cosmological constant, but not the value he wanted for a static universe. It's a value which gives acceleration. On the other hand, if the measurements, as we have some hints of, indicate that it's not that the dark energy density changes with time, then, well, it could still be accommodated with general relativity, but we'll have to tell what is it. And is it left-hand side or right-hand side, right? We'll have to really understand that. I should maybe just make a remark for those of you who are practitioners, to be very precise by my statements. When you say, does dark energy change with time, I didn't want to make the titles too long, so I just said dark energy. But I do mean the dark energy density, okay? In a centimeter cube, with time, what's a change? And even if it's a constant W, but it's slightly deviated from -1, you'll get variation with time for density, okay? You can see it from the equation I had on one of the first slides. So even if it's a constant, let alone if W is not a constant, then of course the density changes with time. Thank you.
Okay, so we have more questions. This is from Mr. Tejinder Singh, Tata Institute of Fundamental Research. Subir Sarkar and collaborators have argued that there is a cosmic dipole anomaly. The magnitude of the dipole is in distribution of radio sources disagrees with the CMB dipole. They conclude that the Copernican principle does not hold, and hence the inference of dark energy is questionable. Could you please share your view on their work?
Yeah, thank you. Well, I know and highly regard Professor Sarkar from Oxford. I know him well, and indeed he and colleagues have pointed this dipole that you mentioned in the radio sources. There have been a number of papers on this. Again, it's a few. I cannot remember what is the current number of sigmas of deviation, but it's again something like maybe 3-4 sigma. And it's always tricky. I work on dipoles in my PhD, by the way, way back with Lyndon Bell in Cambridge. And it's very tricky with dipoles. You're looking for a symmetry in the sky, and it's sufficient for some, systematics to upset things, if the calibration is not the same and so on. So I think it's great that Subir Sarkar and his colleagues are doing that. I think it's very good to check fundamentals. If it becomes a very strong event, maybe we can revisit it. But I would say I'd play I'd be the kind of a broad-minded skeptic here. I mean, it's good it's done, but I think I would not throw away the Copernican principle yet. Thank you.
Okay, sir. If you're comfortable, can we take one or two more questions?
Sure, sure.
Okay, so Mr. Ankur, his question is, what are the main systematic errors that could mimic the signal of evolving dark energy?
Yeah, thank you. So I think to be brief, I think this answer you have to answer it per probe, okay? You cannot just give a global one. So let's start. I think baryonic acoustic oscillations is pretty robust because you just find the position of the peak. You have to do some corrections for the velocity field, but it's pretty robust. So, I'd be surprised if there'd be a dramatic systematic found there, but you never know. Cosmic micro background, again, very precise experiment, and it's reassuring that three different experiments, Planck, ACT, and SPT, essentially give the same answer. But as I alluded to it, there's a paper by Saylor et al. That shows that, in the modeling of the CMB, you have many free parameters there. Then, if you put this optical depth to ionization tau, you change it, you may get something different. So you can think of it as a systematic to dark energy in the way you presented it. Probably the one that I feel a bit worried about, I mean, supernovae are amazing. They're amazing. And basically, they've done an amazing job, and the team leaders got Nobel Prize and all that. And broadly speaking, the results were confirmed. But, supernovae are messy objects. There's a lot of physics we don't fully understand. I mean, we can explain about Chandrasekhar mass and so on, but what's going on exactly, we don't know. Do supernovae vary if they are near the center of a galaxy or the outskirts, if they live in elliptical galaxies, spiral galaxies? So there have been many papers that looked for issues there. I think the good thing that new data coming from the existing protocol ZTF, Zwicky Transit Factory, and of course from LSST, although this would be higher Petri supernova, but the numbers will be so huge to be able to do it for different subsets, then maybe also the theory would get improved. Thank you. That's going to be a fertile area, understanding systematics. Yeah.
So we have two more questions, sir.
Sure.
So this question is from Devjit. Quantum theory tells us empty space is filled with virtual particles. Is dark energy connected to quantum vacuum fluctuations?
Yes, so at least hand-wavy way of thinking about it, and I'm not a particle physicist, is really that in quantum mechanics, we know from the basic course in quantum mechanics, one of the bizarre elements of quantum mechanics that it gives an energy of the ground state of harmonic oscillator, half h nu. And then, so you can't, even the vacuum is energy, and then you can integrate it, and you get this 10 to the power 120 of the density. So that's very intriguing. I think it's such a big problem that people don't discuss it at conferences. It's a huge problem. And I think there's a connection there. There's a paper I really like, which appeared before all this data about dark energy by Steven Weinberg, 1989. And he goes through all these arguments. It's quite remarkable. He did it so early. So it has a nice section there about that. Thank you.
So the next question is from Devjit, DMC College, Kolkata. Oh, sorry, some anonymous one. I recently read the paper you cited. A strong progenitor age bias in supernova cosmology to alignment with DAISY bio and sign of a non-accelerating universe by Jason et al. MNRAS, the suggestion of a potentially non-accelerating universe seems to challenge the standard interpretation involving dark energy. Could you elaborate on how robust these signs of a non-accelerating universe are? Specifically, how should we interpret them in light of existing evidence from supernova and biomeasurements, sorry, and do they point towards new physics or unresolved systematic in current cosmological models? I'm sorry if I not taken a few words properly.
No, that's okay. We say in the jargon we say BAO, baryonic acoustic oscillations, but that's okay. Well, thank you for the question. I alluded to their paper very briefly. Sonnet, it actually got quite a lot of publicity. It's a group that is based in South Korea. So there are two points here. One is it's very good that this group and other groups look into all these details. So they're looking at the correlation between the age of the progenitor, and they show some correlations. Okay, but I would say, and that's the view. I talk to people who do supernova for a living, people who do so. They tell me that the evidence for those correlations between the luminosity of supernova and the host in that paper are not strong. Okay, they may well be there. It's a quantitative question how strong it is. So that's the view of some supernova experts. But personally, I think it's very good that this group in South Korea and other groups are looking into this. And as I said, people look at all other correlations of with the environment within the galaxy and so on. I think it's all very good. Part of your question referred to the fact that it's true that if you take their procedure, fate as it is, they find that the universe is actually decelerating in recent times rather than accelerating. So that's an interesting comment. By the way, there's a combination of BO and CMB that also gives that, but it doesn't get much enough attention. So yes, there are two elements in their paper. One is, is this correlation real? And if it's real, do we actually end up with a decelerating universe? So I would say it's food for thought, but supernova experts are a bit skeptical of the correlations. Thank you.
Okay, thank you so much, sir. This is very engaging discussion. We, however, have many more questions from the audience, lots of pressure on me, but due to limited time, we would like to move to next
Sure, I
session.
understand.
Conclude this session.
I should say that all the questions were spot on. These are really questions that we're all struggling with. So they're very good questions. So I appreciate that. Yeah.
And sir, on behalf of the Bhaktivedanta Institute and all the audience, I would like to once again express our sincere gratitude to you for sharing deep research with all of us. I'm sorry this background sound. This lecture undoubtedly was both rigorous and deep. Even a non-physicist like me now understand how important the lambda phase is. Thank you very much, sir.
Thank you. And I hope if that's okay, I'll stay to listen to Professor Eastman his talk now. Yeah. Okay. Thank you.
Sure, sir. Thank you so much. Now moving forward with today's program, our next speaker, Professor Timothy Eastman, brings a perspective that sits deliberately outside the dominant cosmological consensus. Once again, I would like to request all the participants to please scan the QR code displayed on the screen previously or here to submit your questions to the speakers anytime during the and after the lecture. You may take a screenshot or a photo of the QR code, and there is Google form link has been shared in the chat box also. So it is my great pleasure to introduce our distinguished speaker, Professor Eastman. So Professor Eastman earned his PhD in physics and geophysics from the University of Alaska in 1979. He is an independent researcher in plasma and space physics and philosophy. His scholarly works have encompassed research and consulting in space physics, plasma applications, and space weather data systems since the 1970s. In 1975, he discovered the low latitude boundary layers of Earth's magnetosphere and has since published over 100 research papers in space physics and related fields. While serving as a program officer at NASA 1985 to 1988 and the National Science Foundation NSF from 1991 to 1994, Dr. Eastman was coordinator for major interagencies and international programs. Concurrently, he carried out research in philosophy, publishing over 30 papers, and served as lead editor of Physics and Whitehead and Physics and Speculative Philosophy. His current research is focused on a synthesis of recent developments in philosophy, physics, logic, semiotic, and process thought as articulated in his book, Untying the Gordian Knot, Process, Reality, and Context, which contributes to a new natural philosophy for the 21st century. Dr. Eastman's latest essay include traits as primal and orders of possibility and actuality. It is so for his talk today, plasma cosmology. It does not merely propose an alternative model. It raises a more uncomfortable question. When does a framework become so dominant that alternatives are no longer explored with equal seriousness? Dr. Eastman, we look forward to your insight. Over to you, sir.
Well, thank you. Let me get this put to full screen here. I'm not trying to arrange to full screen. Here we go. Okay, can you see the screen okay?
Yes, sir.
Okay, let's see, I need to go to the first. So, as noted in the introduction, my background is in space plasma physics with a focus on solar system plasmas from the sun to the outer planets, but especially the sun magnetosphere interaction and with application to solar terrestrial relations and impacts on technological systems like impacts on GPS satellites and other satellites. All satellites, anything to the ionosphere and beyond, are in a plasma environment dominantly, and so return currents and spacecraft charging and other effects like that need to be handled, and that's where we study studies of space plasma within the solar system, where we do direct sampling with spacecraft, and that's an ongoing enterprise. But it's only within the solar system where we have made direct in-situ sampling of data, and but astronomy more broadly and astrophysics is by just remote sensing. So then as I got into working with some more fundamental questions in philosophy, I've done this work on tying the Gordian knot that came out in 2020. And also an essay following that from Perry perspectives, orders of possibility and actuality, which is relevant to some of the foundational philosophic questions. By the way, thanks to you for this opportunity to present as part of your golden anniversary, and congratulations to all for that anniversary. Let's see, it's not advancing. Let's see. Yeah, I'm not sure why it's not. Here we go. It did not respond the first time. Okay, I'd like to dedicate this to important scientist in India, Jayant Narlikar, who passed away this past year. He had done work with Hoyle and others, important work, especially worked with the steady state model, but an alternative model, an outstanding physicist. And to Dr. Nalekar, I dedicate my presentation as an example of alternative approaches to these various issues. The key points I wish to make here in this presentation is attention to how there's various predictions of the Big Bang research program that appear to fail, that we need to pay serious attention to certain alternative models. And I've concluded from my own investigations into this that based upon an orientation to a understanding that incorporates both gravity and electromagnetism and plasmas, that we come to possible framings in which there's no clear finite origin of the universe. It may be of indefinite age, that we really need to address not just gravity, but gravity and electromagnetism and plasmas at all scale, that filamentary space plasma systems occur at all scales because there's certain scale invariant characteristics. So it's not just in the solar system scale in which my research is focused, but really it's relevant at all scales. And this is reflected in a number of major essays and books in plasma astrophysics that have appeared, especially in the last 2 decades. And also I'd like to call attention to the fundamental issue of redshift. And a recent breakthrough about that has occurred with work, for example, that by Dr. Marmet, which will be presented early tomorrow in day 4 on quantum spectroscopy, which really changes the issue about how we think about the redshift, that it may not just be oriented to an expansion redshift, that there's important non-expansion redshifts we need to consider. And then the other thing is the issues of fundamental philosophic and issues of philosophical ontology. So I think that represents a sixth fundamental point, that how do we think about the fundamentals of these theoretical frameworks that we have? And in my own work, I've come to conclude that there's need to not think of the fundamental order of things as a real order only of space-time actualism, but a distinction of the order of actuality, observed space-time diversity, and an order of possible relations related to quantum pre-space process. And this in turn requires some kind of grounding, a unity. We might think of that in terms of Brahma, a great tradition of Indian philosophy. So in my framework of natural philosophy, I've put together Untying the Gordian Knot. It pulls together developments within the past few decades in quantum physics, triads of input, output, context, logic, complex systems, semiotics, and process thought to illustrate how potential relations, both local and local global, provide a grounding for causation, emergence, physical relations, a new way of thinking about the fundamental basis of time, and its ways of knowing incorporate both context emphasis and context independence, the latter science and the former arts and humanities. And this framework also includes a role for ultimate context, that is, meaning in the spiritual dimension. Now, I think when I get back to fundamental logics, that we usually think in terms of Boolean logic, a logic of actualization, which there's only 2 values, either on or off, like in digital computers. But really, when you look at the quantum physics, the fundamental process, that one has to refer also to a logic of potential relations, or potentia, a non-Boolean logic or free logic that allows for not just 1 or 0 on or off, but also the in-between, the maybe. And arguably, quantum physics requires both a logic of actualization and a logic of potentia, unless one insists on actualism and appeals to multiverses ultimately. So essays on this recently have been published by Kastner, Kaufman, and Epperson, taking Heisenberg's potentia seriously in IJQM in 2018, and Hans Primus, Knowledge and Time, in 2017, and others. So in my own framework, then I really step back and think of the real as both the actual and the possible in terms of an ontic understanding. and that physical laws or relationships, that laws is like a misnomer based upon reference to legal frameworks. To me, it's just a misnomer. It's really fundamental. Physical relations are constraints and possibility as reflected in the power of principles of least action. So at the most fundamental onic levels, I would argue that there's a quantum substratum or pre-space, a veiled reality, as well as the actualized space-time quantum world, experiential now. And as a subset of this space-time description, classical models are exceedingly good approximations, but they're not a basis for fundamental ontology. I'd argue that also quantum process is fundamentally triadic. This is brought out in a paper I've done in Process Study Supplement recently, where it can argue triads as primal. You can think in terms of a triadic of input, output, context of any system. That systems in general are semiotic in the sense of Charles Sanders Peirce, not just a simplistic input-output dyad. So in terms of the more basic ontology, I'd argue that we have process, which is input-output succession within context that's reflected, say, in quantum field theory, and in fundamental logic, the logic of actualizations and the logic of potential relations, and the relations more fundamentally in terms of part, whole, local, global, internal, external, which then encompasses the domains of semiotics and category theory, which is a algebra of most fundamental of mathematics, so to speak, a type of fundamental algebra of relations. So with regard to getting to the issues of from quantum to cosmos and connecting these philosophic points to the cosmological questions, an interesting recent development has shown from Andrea Schlatter and Ruth Kastner that Einstein's gravity physics can be derived from quantum physics and in that sense is not equally fundamental as presupposed for the past century in trying to get at some kind of approach to a unified field theory. That whole effort for the past century has been grounded on the notion that they're equally fundamental, but arguably from this development and a couple of developments like this in the past decade suggest perhaps that's not the case. Further, in contrast to the Big Bang research program in which multiple hypothesized entities such as dark matter, dark energy, inflation, and black holes have evaded observational test, direct test, or confirmation for decades, and for which it's difficult to identify cases of in advance prediction where it's followed later by the actual observation versus, say, simply various modes of finding consistency. I outline here a new understanding that is evolving by several parties of a gravity plus plasma model, electrodynamics and plasma, that doesn't require any such new physics and that can nevertheless appear to, more and more to basically explain all basic cosmological observations, including the most recent observations representing exceptional challenges to the popular Big Bang model. So to remind ourselves about the primary naturally occurring systems out in the world, it's often described in terms of states of matter, solids, liquids, and gases. But I think in terms of systems, condensed matter or compact systems mapped to solids, fluid systems in general, which we described in the Navier-Stokes formalism, encompasses a neutral gas and liquids. But there's also a third fundamental system, electrodynamic system, based upon the Maxwell-Boltzmann formalism and related that maps to plasmas and plasma systems more broadly. And plasmas being in the universe by sheer volume and by total mass are dominant, arguably, but not so, fortunately, right here at home near Earth. Now, space plasma physics, space plasmas are multi-scale from lab to solar system to galaxies and beyond. And Goodluck and Poets in their Principles of MHD from Cambridge have argued that the nonlinear interaction of plasmas and complex magnetic structures involve large-scale tubular magnetic structures moving with the plasma so that magnetic forces are transmitted with the fluid, one could hardly imagine a larger contrast with central electrostatic and gravitational forces decaying in vacuum with distance of 1 over r squared. This relates to how, as we've looked out with recent data from Hubble and JWST, that we see filamentary structures and structures at multiple scale, essentially without limit. So as some elements of what I think of as the plasma universe, here's a picture with a chronograph of the stellar chromosphere with the arched plasmas coming out, aligned with the magnetic field, so dramatically illustrating the magnetic field of the Earth. And here's a coronal mass ejection, seeing an X-ray over to the right of this figure, superimposed with a coronagraph picture of the sun at the same time in ultraviolet. And here's an artist depiction of the Earth and its magnetosphere. The Earth is embedded in within its the ionosphere and magnetosphere system that is the solar wind from the sun side presses in and creates a collisionless bow shock. And then there's boundary regions that then provide the interface from the solar wind to the magnetosphere, and it's stretched out as a long magnetotail. So literally the Earth is like a great comet. And so to speak, every obstacle in the solar wind flow coming out from the sun in all 3 directions, every planet, every moon, every obstacle is such a cometary-like interaction. So cometary-like interactions are very pervasive, indeed, not just in the solar system, but everywhere. So characteristics of plasma are they're multi-scale, there's filamentation, there's directionality, they're conductive, and the highly interactive. This shows an example of that of the CME coming towards the Earth, then inducing a solar storm that provides enhanced aurora. The auroras are always present, just that most of the time we can't see them, but they're always there. And plasmas are multi-scale. Here's an illustration in temperature range and number density. The plasmas in some form or other occur essentially all scales. Here's various examples by Aurora showing the filamentation and fine structure that we observe as the electron precipitation creates aurora as the plasmas from the outer magnetosphere maps down. And directionality sort of symbolized by the fact of lightning that we experience, all of us. How it conducts electricity, that a plasma medium, that's one of its key characteristics, the ability to conduct electricity in addition to just to exhibit collective effects in general, and the interactivity of plasma systems. Here showing a model of Earth with its ring current and magnetosphere system and the fields associated with it. Now, there's been a focus on gravity in astronomical research for much of the past century. That's largely appropriate, but I think we need to get beyond that. Cosmology and astrophysics have traditionally focused on neutral bodies and gravity. However, the approximation of plasmas of fully shielded ionized gas, which is good to 1 in 10 to the 5th, 1 in 10 to the 6th, and so forth, is implicit in simplistic references to gas and not to plasmas. However, it's only an approximation. It's only and it's a limited approximation, and to treat it as 100% fully shielded is simply invalid everywhere direct space measurements have been made. There are 2 important long-range forces relevant to astronomy, both gravity and electromagnetism. Now, we sometimes forget some of the limitations of modern cosmology. One is that we currently lack a unified field theory, understanding deeply the connection of gravity and quantum theory. The cosmology is intrinsically an historical science and lacks direct experimental testing. That the data in cosmology are generally limited to remotely sensed photons. There are no direct in situ measurements as possible in solar system-based plasmas, the area I've worked in, where we do both in situ as well as remotely sensed. But that's simply not possible in most, astrophysical and cosmology systems. And most existing cosmology models focus on only one long-range force field, gravity, and basically ignore the effects of plasmagnetism, assuming incorrectly that such effects are 100% shielded out. And commentary and some data relevant to that come up frequently in the cosmology group at cosmology.info, which I recommend in terms of it's a group of scientists that do compilations of papers that raise questions and point to possible alternative needs for alternatives. Now, looking for surveying the various alternatives, I've come to conclude that one of the most promising alternative approaches is Eric Lerner's galactic origin of light elements model. And the benefit of this kind of model is to argue, well, one thing is a matter of the predictions he's done. For example, Lerner and Scarpa in April 2022 predicted specifically that the JWST, when it went up in July 2022, when its data would come out, this is an in advance prediction. They predicted that there would be fully formed galaxies observed at all scale, at all redshifts. That was a specific prediction of the model, which is specifically in contrast to what was expected from the standard lambda CDM understanding. And indeed, it turned out we're seeing fully formed galaxies as they predicted. They also argue that all light elements are created by thermonuclear and cosmic ray processes in young galaxies, as confirmed by observations. Lerner states, for example, that Big Bang predictions are contradicted by at least 16 data sets, whereas elements of his model, predictions of his model, appear to be contradicted by none. And he argues that this model requires a non-expansion redshift, whereas most cosmological models require an expansion redshift. Well, indeed, it turns out that that a real non-expansion redshift appears to be the case, as Dr. Marmot will describe early tomorrow. Continuing on. So one thing that was a specific prediction by in Lerner's approach to this is the classic Tolman test for galaxies, the surface brightness test. And a specific prediction of non-expansion with approaches on the surface brightness test is that the surface brightness should be unchanged with redshift, whereas the Big Bang model has a exponential prediction compared with that. And so here's a plot of surface brightness versus redshift based upon all the Hubble data in a paper published in 2018 that shows a very clear contrast between the prediction of non-expansion mode versus Big Bang prediction. Now, this has been extended recently with JWST data up to redshift 10, and it's continuing to maintain this surface brightness at the same non-expansion predicted level. So Narlikar and Burbage back in 2008 did raise the question. That's today the most basic question is, do we really understand the nature of the redshift? And we find that non-expansion redshift can be due to electron plasma in intergalactic space, and treating this enables successful predictions of electron number density, dispersion measure, the cosmic background radiation, and the Hubble relation. This has been laid out by Lyndon Ashmore, for example, in a work he has published in 2016 and further described in his work Tired Light, came out in 2016, where he had made a prediction about the electron number density and dispersion measure about 2005, and then the final result came out in 2016 confirming that. And now he has an argument showing how from first principles he can get not just those, but also the Hubble relation. And the correlation of this would be entirely unexpected from a standard Big Bang approach. And also finally, for non-expansion redshift, quantum spectroscopy laboratory research reveals a spectral transfer redshift providing coherent, that is non-blurred redshift based upon modern quantum electrodynamics and laboratory testing. This is not now a Compton shift, which would give you blurring. This is a coherent, non-blurred type of redshift. So Eric Lerner has calculated that the big ring interpreted as a rotating electromagnetic plasma helix system using his 1986 model would be expected to have a radius of 1.2 billion light years. And then observation by Lopez, Close, and Williger has reported a big ring in the sky from their observations of quasars and seeing structures, one complete ring that appears to clearly be ordered. And Eric had predicted a radius for such extreme structures of 1.2 billion light years, and what's observed was 1.1 billion years. So a surprisingly similar result to what was predicted back in the 1986 paper. Notably here, the Big Bang size limit is roughly half the size of this blue ring. So the issue is when you put together both gravity and electromagnetism in plasmas and consider, well, what happens at multiple scale, you would expect to have clumping at all scale, structures and filamentary structures. Indeed, space observations have continued to reveal multiple levels of structure without limit, of which the big ring is just the latest example. This result clearly suggests that the cosmological principle of homogeneity and isotropy at the largest scales, a critical basis for the Big Bang research program and for applying the solution of the Einstein equations, which requires homogeneity and isotropy, doesn't really apply to the real cosmos. Now, with regard to force-free magnetic vortices, there's a pinch effect in space plasma that inevitably creates vortices at multiple scales. And given enough time, this will be at scales to stellar scale, galactic scale, and beyond, illustrated here by the Vela Nebula. And arguably a combination of both electromagnetism and plasma effects and gravity over time, over billions to trillions of years, can create a hierarchy of structures, in turn creating superclusters, clusters, galaxies, stars, planets. And Lerner has argued that in the long term, this process represents an evolutionary building up the cosmos, not a running down. A building up because gravity provides that integration over seeding long time scale, but then eventually gravity yields stellar systems that then compress to ever larger densities that then ultimately give you the fusion process. And the fusion process then can be a source of free energy to then contribute to the formation of new structures at the local scale. So it's interesting from Narlik and Burbage, from their work, Facts and Speculation of Cosmology of 2008, they noted that the day or night of Brahma, the creator of the universe, some 4.3 billion human years, thinkers of the day did think of timescales far in excess of normal human lifespan. And in my Perry paper, I noted our fundamental ontology now incorporates both an order of actuality and an order of possibility, the former indicating a radical diversity, the latter possibilities that amplifying diversity. And yet such ultimacy and res potentia requires a grounding, perhaps a kind of unity suggested by arguments for the absolute necessary of dimension of being, such as notions of Brahma. Now, one thing I've argued in my work, dualities without dualism in Whitehead and physics and other areas, that classical sciences tended to focus on one side of a dual pair: substance focus, external relations focus, symmetry focus, determinism only, particles only focus, and so forth. But that contemporary science arguably is both external and internal relations, both symmetry and asymmetry, both space and time, both parts and wholes. So a way in which any polar player is relatively balanced with neither term simply primary. And this is, I think, an important development in philosophy of science over the last 200 years. And here I lay out a way of thinking of the transition from classical physics and its implications in the 19th century and before to modern physics, where one puts together a standard view that, in a way, brings together classical metaphysics to the new physics of quantum and relativity. But it's a mixed view because it's borrowing from that classical metaphysics. But I think as we come into the present century, we're really getting into more of a process and relational framing of things that includes not just understanding waves and particles, but networks of relationships, in which and then also involving a logic of not just a logic of actualization, but also a logic of potentia, both Boolean and non-Boolean. With that, thank you very much.
Thank you, sir. Uh, uh, Thank you for this stimulating and modest presentation, sir. It was such a smooth transition from plasma and cosmic process to Big Bang prediction to quantum cosmos to limitations of modern cosmology and so on. May I now request the team for the question and answer session? A gentle reminder to the audience, if you want to bring some questions, you can submit in the Google form link that is being shared, and can use the QR code also that is being shared earlier. And now I'm coming to the first question by Mr. Rajesh. Does deriving gravity from quantum physics resolve the conceptual tension between general relativity and quantum mechanics, or does it simply shift the problem to a deeper layer?
Well, it's a very good question. And so, yes, I think now we have the conceptual tension because we're treating them at the same ontological level. And then you find this incompatibility between a theory which is fundamentally continuous versus one which is not fundamentally continuous in framing. But now, in terms of thinking of it as derivative in some sense from quantum field theory, then that, I think, resolves that technical scientific tension. But at the same time, in fundamental quantum process, to understand that and understand the problem of measurement in quantum theory, I think we necessarily have to see a way to handle the two logical orders I speak of, that of both actuality and possibility, both Boolean and non-Boolean. Thank you.
Moving to the next question. So it is from Kumar Ravi from Swami Vivekananda University, West Bengal. It seems to me that the Big Bang theory is sometimes seen as aligning more naturally with certain Western philosophical frameworks, and that many Western economic ideas are likewise shaped by deeper philosophical and theological traditions. In that context, how do you view quantum mechanics? Do its features such as indeterminacy, non-binary behavior, and observer dependence have any genuine philosophical affinity with classical Eastern traditions, or are such parallels mainly interpretative? And in this light, how should we think about cyclic cosmology?
Well, that's a very good and fundamental question about the way in which there's been a tendency for a distinction of Western ways of framing things and some Eastern philosophic traditions, both India and China, et cetera. And so I think we have so much to learn between the two. And yes, there's been and I think there's elements of this more inclusive framing that I speak of, this duality without dualism, that gets reflected in Eastern and Western traditions. And it goes back to early encounters between East and West. For example, with Leibniz, who recognized that the tendency toward more process relational framing of things in certain Chinese and Indian narratives and traditions, and so it has a long, this whole recognition has a long history, and there's more to be learned from that. Thank you.
Thank you, sir. We have one more last question, maybe for this session. So this question is from Jagdishwar. Standard cosmology treats gravity as the sole driver of large-scale structure. At what specific scale length do you believe electromagnetic forces begin to dominate or significantly overrule gravitational collapse in the evolution of cosmic filaments?
When you get there's a so the electromagnetic effects, electromagnetic plasma effects, are especially present at relatively low density when it's a non-collisional. And throughout the solar system, in the area I worked with, we have a collisionless space plasma. So and gravity is completely negligible. Then when you over extreme long time intervals, say have a coalescing astrophysical system in which these plasmas are gradually being brought together by gravitational force over long lengths of time. Eventually, it would get to a density which would transition from collisionless or semi-collisionless to collisional, and then that collisionality would then enhance the neutrality of the system, and the gravity would really become dominant. Then you go into the phase of the formation of a stellar formation. So it has to do with the transition from collisionality, from more collisionless condition to the more collisional, transition to a more neutral, to fully neutral state. But typically in a collisionless, much of the, by volume of astrophysical systems are subject to the electromagnetic and plasma effects, are not so dense. But when you get to the more dense system, then of course gravity is dominant.
Okay, sir, can I take one more question with your permission? Yeah.
Of course.
This is from Dr. Aristotle. What are your thoughts on inherent teleology in the cosmos, given the structure in the development of the universe? More importantly, in the broader framework of worldview as a system of fundamental domains of knowledge of human existence, how does teleology play a part?
Yeah, that's an interesting question about the purpose and such fundamental notions, and it's a philosophic even issue of ontology. And so I think I like the name Dr. Aristotle. I wish I could dialogue with Aristotle about all these issues and Plato. But I think there is some intuition here. Is something happening with regard, if we're forced into recognizing, as I argue, a fundamental order distinction between the actual and the possible, that there's, say, in quantum physics, we're forced into recognizing some pre-space, not just simply actualized output of a system, that you're going from possibility to potential given constraints on the possibility to specific actualized outcome given measurement. And if that's a fundamental process, then then the possible relations are is a distinct fundamental order, arguably, both non-Boolean and Boolean. If you have that, then the real is not just the actual, but the real is the actual and the possible. And for the real that is the set of the possible, then arguably it has to be a grounding for that set of the possible. And what is that grounding? Well, that's a suggestion of a pointer to a unity, a pointer to some grounding, some entity providing a grounding. That suggests, well, we don't know. To me, that's a philosophic and metaphysical thing that we're in a way driven to by the science. Thank you.
Okay, thank you very much, sir, for maintaining both rigor and openness in the discussion. We still have time, but I would like to conclude this session for now. We will move to the final session of this day, and on behalf of this Bhaktivedanta Institute and all the audience and participants, I would like to once again express our sincere gratitude to you, sir, for this thought-provoking lecture. And it was very interesting and discussion today for all of us. Thank you, sir. And now may I see we have some time, and our next lecture is on the nature of the universe, the big picture. So, but it is scheduled at 7 p.m. We have 10 minutes in our hand. So may I request Professor George if he is ready for his presentation at this point, or shall we wait for take a bio break for 10 minutes up to
whichever you like. It's up to you.
So we are open to continue this discussion, and if you are ready, then we will proceed.
Okay. I'm going to.
Okay, sir. So shall we proceed for your lecture, sir?
Yeah. Sure.
Okay. So
can you see that?
Yeah, I can see you. I can see you. So let me formally introduce you, sir, to our participants. So for this third lecture of today's session, our speaker is Professor George Ellis from the University of Cape Town. He'll be speaking on the topic, the nature of the universe, the big picture. So before we proceed further, I'd like to request all participants to please scan the QR code displayed on the screen to submit your questions to the speakers anytime during and after the lecture. You may take a screenshot or a photo of the QR code. Also, there is a Google form link that is shared in the chat box for your use case. It is distinct honor to introduce Professor George Ellis. Professor Ellis is the Emeritus Distinguished Professor of Complex Systems at the University of Cape Town and one of the world's leading theorists in cosmology and general relativity. He is the co-author alongside Stephen Hawking of the seminal monograph, The Large-Scale Structure of Space-Time, which established the rigorous mathematical foundations for understanding black holes, singularities, and causal geometry of the universe. A fellow of the Royal Society and past president of the International Society of General Relativity and Gravitations, Professor Ellis has been instrumental in defining the physical laws that govern the cosmos. Beyond his contribution to physics, Professor Ellis is a profound thinker and deeply questions the validity of reductionistic framework with his theory of top-down causation. He demonstrates how complex systems, including the human brain, can causally influence underlying physical matter, providing a scientific framework for understanding agency and ethics. A recipient of Templeton Prize and the Order of Makbungwabe, sorry for pronunciation, from the South African government. Professor Ellis is a leading moral voice in science, advocating for the synthesis of rigorous empiricism with a deep appreciation for the philosophical and ethical dimensions of human existence. His lecture, The Nature of the Universe, the Big Picture, invites us to step back from competing models and reflect on the boundaries of scientific explanation itself. Professor Ellis, it is a privilege to have you with us. This virtual platform is yours now, sir.
Thank you very much. Great pleasure to be with you. I tried to share the screen. It doesn't seem to be up there. Okay, can you all see that?
Yes, sir. We can see it.
Okay, good.
Could you please do it in presentation mode for this slideshow mode, so that it will come an entire screen?
Oh, okay, yes. Sorry, slideshow. Yeah, okay.
Alice, if you go in the bottom of your screen, or on the right side, you see on the right side, from the right, go down, yeah, or more down. There you see the first icon on the right. No, bottom of the screen.
Bottom, sir. Yes.
Yeah, left. You go, no, you go left. You are at the right place.
Sir, there's an icon where this minus sign just adjacent to the minus sign, and if you put yes, sir. So just adjacent to the minus sign, sir, this icon, if you click it, no. Sir, this is for the zooming in and out, and just left side of this minus sign, there is an icon. Yes.
This one, yeah.
Okay, is that right?
Yeah, it's now.
Perfect.
Thank you, sir.
Okay, so our ancestors look up at the sky and ask questions about our existence. And the questions are, what are stars made of? Why do some of them move? What's the nature of the Milky Way? And are we at the center of the universe? And how did it come into existence? And all of this I used to ask. And this was before we knew the distance of the Milky Way, before we knew that the Milky Way was a whole set of stars. And this is this beautiful picture of the astronomer trying to look out and find out the way it works. Now, I'm going to have three parts to this talk. First, I will summarize the current canonical understanding of the physical nature of the universe, together with their limits. Second, I will reflect on the limits to knowledge about the physical universe. And third, I will consider some issues that go beyond what science can say, and including what kind of meaning is there in the universe. So the universe has physical elements that are understandable through physics and through astronomical observations. I'm going to summarize here the current canonical understandings of the physical nature of the universe, together with their limits. And some of your other speakers will question this canonical, but I'm going to present the canonical. The physical evolution of the universe is based on testable physical laws. It's very important they're testable. The physical laws deal with the interactions of particles and fields, and they're tested using laboratory experiments and particle colliders, together with observations of what exists inter alia by using telescopes of many kinds. These laws enable us to our understanding of the physical universe. So the universe is made up of galaxy. Galaxy is billions of stars, and the Milky Way is a galaxy seen edge on. Galaxies come in clusters, and a typical galaxy, this is Andromeda galaxies, 100 billion stars, about 50,000 light years across. If this is very similar to our galaxy, and if this was our galaxy, we would be way out towards the edge over there. The Earth to the Sun is 8.3 light minutes. Proxima Centauri, the nearest star, is 4.3 light years. And so this is 50,000 years, immensely larger than the Earth to Sun or the distance to the nearest star. Now, the universe is evolving with time. Observations of distant galaxies establish that the universe is changing with time. Its overall scale is increasing as galaxies move away from each other. All the greatest minds at the time, from 1917 to 1931, assumed the universe was static. And this was Einstein's greatest mistake. Einstein denied that the universe could evolve. And this truly was his greatest mistake when both Friedman and Lemaitre told Einstein they had evolving solutions. He told them that those were non-physical. The evolution of the universe is governed by the laws of physics, which are the same everywhere and unaffected by our existence. We can't change these physical laws. And the evolution is governed by gravity, Einstein's theory of general relativity. Now, this need not have been the case. This is true because stars and galaxies are uncharged. They have no electric charge. If they did have electric charge, then electricity would govern the evolution of the universe. But because stars and galaxies are at large scales uncharged, then Einstein's theory of general relativity governs what's happened in the universe. The outcomes depend on what matter and radiation is present. And here's the evidence that the universe is expanding from Hubble in 1929. He measured a series of distant galaxies. He measured the K and H lines in the spectra, and he measured the distance given by apparent size. And he showed that that these lines are shifted because of the Doppler shift, because they're moving away from us. So this was evidence that the universe is dynamic, that the larger the Doppler shift, the smaller the thing looks, and therefore the further away it is. Larger distances correspond to larger velocities of recession from us. Now, the concordance model looks like this, and you've all seen this map, and I'm going to step through it step by step to see what happens. Time is going sideways. The start of the universe is over here, and the physical scale of the universe is represented sideways in this picture. Now, there was some kind of start, and I'll return to talk about that. Immediately after cosmic inflation took place, an incredibly short period after the start, the universe expanded hugely by more than 70 e-folds, became very empty and cold. Then reheating happened, conversion of the inflaton field to matter and radiation, and that all took place in a very, very short period of time. Matter and radiation then cooled down, and Big Bang nucleosynthesis took place at about 10 to the 9th degrees Kelvin. Baryon acoustic oscillations took place later, the whole universe acting as a great oscillator, and these both affected structure formation. And Ofer, Lahav gave a wonderful talk about all of this an hour ago. Primordial nucleosynthesis took place, in which you get neutrons, hydrogen, helium, tritium, helium-3, beryllium, and lithium through this series of reactions, and they resulted in primordial element abundance of deuterium, helium-4, helium-3, small amounts of lithium, beryllium, but no heavier elements. So the elements out of which we are made did not come from the early universe. This is a form of downward causation from the cosmic temperature-time relation. As the universe expands, the temperature decreases with time, and that's determined by the cosmological density of matter, and which is rho t. And this is a downward causation from this cosmological scale interaction down to the scale of nuclear physics, as shown in that diagram. Then, as cooling took place, the ionized matter became neutral and matter radiation decoupling took place. Before this, matter and radiation were tightly coupled. After that, they were decoupled. And black body radiation was emitted at a temperature of 4,000 degrees Kelvin. And this temperature decreased inversely with the scale of the universe. So this is when the black body radiation was emitted after about 300,000 years after the start of the universe. And one of the most remarkable diagrams which we have is this one, that the spectrum of that black body radiation has been measured, and the spectrum is a black body spectrum to more accuracy than you can see. The errors are less than the size of this line. So black body spectrum at 2.73 K, a spectacular agreement between theory and observation. And what this proves is that both quantum physics and statistical physics held unchanged at that very early universe. And so this confirms that physics was the same at that time. Now, the isotropy of this radiation, at 1 part in 250, it looks exactly the same in all directions, which is evidence of smoothing of the universe on the larger scales. This is an all-sky map here, and if we assume we're a typical cosmologic observer, so all observers see the same, then it's a theorem that the universe has a Robertson-Walker geometry, which is the standard geometry of an expanding universe. If you go to 1 part in 250,000, at 1 part in 1,000, you see a cosmic background radiation dipole. It's hotter in one direction and colder in another direction. And we interpret by saying we're moving relative to the fresh frame of the universe at 370 kilometers a second. So there's a standard of rest in the universe due to its time-dependent Robertson-Walker geometry. If we remove that dipole, then at 1 part in 250,000, we get these very, very small fluctuations. This is the entire sky. It's an image of the last scattering surface, a temperature variation over the entire sky when we've taken out the dipole. And it's a series of very tiny fluctuations, and these are the seeds of structure at later times. So this is these fluctuations are 1 part in 100,000. This is the image of the last scattering surface. And it's basically random Gaussian fluctuations, which are the seeds for galaxy formation. Now, you can analyze the angular variation of here, break this up into different angular variations, and you get this remarkable series of peaks. And peaks in the angular power spectrum are due to inhomogeneities at different scales in the hot Big Bang era. And theory and observation agree extremely closely. The observations are the dots and these lines, and the theory is these curves. And it is a truly remarkable thing that the theory and the observations agree. It's a great triumph of cosmological theory, and this gives us confirmation that our theories are at a large scale correct. These fluctuations, then there were dark ages when as the black body radiation cooled down and there weren't any stars, but then the first stars, these are the dark ages, the first stars formed, and then galaxies, planets, and all the rest forms at later times. Fluctuations on the large scale surface led to structure formation through gravitational instability. To do so successfully, an agreement with the cosmic background radiation required both dark matter and dark energy. And again, Professor Lahav mentioned both of these, and I'll come back to them again. The fluctuations originated through quantum effects, quantum fluctuations in the inflationary era. And one of the things which is missing in the standard theory is how those quantum fluctuations become classical. And this is one of the great big scandals in the standard model. There were quantum fluctuations, they weren't classical. By the time you hit the last scattering surface, they are classical. And how that transition took place is a missing element of the standard model. Now, then stellar nucleosynthesis took side and side stars, and in stars you had this onion structure of shells, hydrogen, helium outside, helium, neon, then helium, carbon, neon, oxygen, carbon, oxygen, neon, magnesium, silicon, and then iron and a nickel core. And this is one of the triumphs again of theoretical astronomy, is finding out that all of these nuclear reactions were taking place inside the star. This is a massive star near the end of its lifetime, where it has this onion-like structure just prior to expanding as a supernova. This is again an example of downward causation. The temperature, density, and fractions of elements vary with radius at the macro level. They determine outcomes at the micro level. So they're different nuclear reactions at each radius. And this is an example of what's happening at this particular radius. And so the macroscale structure is determining what nuclear reactions took place at the microscale. The first generation stars create elements up to iron and nickel by stellar nuclear synthesis. And some of these ended their lives in massive explosions, spreading these elements through space. Second generation stars formed from this debris. They had accretion disk around them containing these elements. These led to the existence of planets, which contained the key elements of life: carbon, nitrogen, oxygen, phosphorus, which had been created inside those stars. Hence the famous phrase, "We are stardust." Now, so you had all of this taking place: stars, galaxies, planets, and so on taking place. First generation stars, second generation stars, and then eventually the speeding up of the universe, the dark energy leading to accelerated expansion. And this was discussed in depth in the first lecture this afternoon. A completely unexpected anti-gravity effect, because ordinary gravity always causes things to collapse. Here, something was making it not collapse, and that was dark energy or cosmological constant. And the evidence here, the supernova cosmology project, this curve isn't straight, it was expanded to bend down, but it actually bends up. So the late time speed up of expansion must be called some form of dark energy, which may change with time when it's called quintessence. Or it may just be the result of a positive cosmological constant. And at present, that's a viable option. So this is distance against redshift, and it's the curve is bending up when we expected it to bend down. And this won the Nobel Prize towards the end of the last century. The present-day age of the universe is 13.7 billion years since it started. And this is big enough that there's no age problem for stars and star clusters. One of the major things you have to do in cosmology is check that your theory of stellar formation doesn't result in stars having a bigger age than the age of the universe. And for a long time, in fact, this was the case, because the Hubble constant was wrong by a factor of more than 2. And so for a while, we actually had a situation where cosmology was inconsistent, because some of the stars clustered were supposed to have an age bigger than the age of the universe. Now we have recalibrated the age of the universe, and there's no longer this problem. Now, if the age now is 13.7 billion years, so what will this diagram look like at 18.7? What will it look like in another billion years? And the answer is, this right-hand edge of this diagram will have moved a billion years to the right. In other words, we live in an evolving block universe, a space-time which has a future edge, and that future edge is moving with time. And at present, from the start to here, it's 13.7. In a billion years, it will be 14.7 billion years old. So at later times, the space-time itself is extended. It is larger than it was at earlier times. Now, what will happen in the future? Will it keep on expanding, or will it collapse? Well, will it collapse to infinity at a finite time, which is called a big rip? As far as I can believe, I don't think there's any likelihood whatever that it will collapse, because the dark energy is far too large for that to possibly happen. What is likely to happen is the universe will just keep expanding forever. It won't expand an infinite amount in a finite time, which is called a big rip. I think that's completely unphysical. Almost certainly neither will happen, the collapse or the big rip. Almost certainly it is likely fated to extend forever, with the temperature going to naught, which used to be called the heat death. So we have a very successful database model. All the observations converge to the same set of cosmological parameters. They lead to the lambda cosmological cold dark matter standard model of cosmology, in which the universe is very nearly spatially flat. Energy density is 71.4% dark energy, 24% non-baryonic dark matter, 4.6 baryonic matter, and the age 13.8 billion. Now, non-baryonic dark matter, this was very, very unexpected as well. In order to make, this is required in order that the structure formation studies and the microwave background studies fit together, and they do fit together pretty well, provided you have the dark matter. And this is matter which does not interact with baryon, which is why it's called dark matter, because you can't see it. It only interacts gravitationally. So, multiple issues. The big 5 issues is what's the nature of dark energy? And we simply don't know. And that was discussed at length. Now, one of the things which our theory should not allow, that should be allow W less than -1, negative inertial mass density. And many analyses of dark energy, in fact, allow W less than -1, which is that the density plus pressure is less than -1. Now, to my mind, that is completely unphysical and cannot happen in physical reality. So in my mind, when you're examining the nature of dark energy, you should forbid anything to happen like that, because that's unphysical. You should exclude that from your analysis. Now, what is the nature of the invisible dark matter? And it's not ordinary matter, and we simply don't know what it is, and a great many examinations are taking place to see that. What's the nature of the inflaton that powered cosmic inflation in the very early universe? And we don't know. And we've actually got about 200 models of what the inflaton might have been. So these are the big 3. Now, then why is there an inconsistency between the near and far Hubble parameter estimates? Is it a systematic error? Do we need modified gravity or inhomogeneity? And we simply don't know which of these the problem is. So there is a problem. It's not enough to say, it's not a big enough problem to say that the whole model is wrong, but there are various possible ways that this could be resolved. It might be a systematic error in the measurements. It might mean we need modified gravity. It might mean we need inhomogeneity, make an element of inhomogeneity to make everything work. And what this emphasizes the need for consistency tests of the standard model. One of them is, is a perturbed Robertson-Walker geometry actually a valid description, or do we need an inhomogeneous model? And there's a test which I made up, which I discovered with John Baldwin many years ago. I mentioned the dipole of the microwave background radiation. There has to be an equivalent dipole in all measurements of number counts. And if that equivalent dipole doesn't exist, then something is wrong with the standard model. And the final problem is, how did galaxies and black holes form so early in the universe's history? And this is a big puzzle. With the James Webb Space Telescope showed that we have galaxies and black holes very early in the universe, and it's a problem how they formed so early. Now, there are many unknowns in addition. The first is, what's the spatial curvature? Is the universe positively or negatively curved? And many analyses don't even try to determine what this curvature is, but it's a key parameter. If the curvature is positive, then the universe closes up on itself, and it has a finite amount of matter, a finite amount of galaxies, and it closes up spatially. If it's positive or negative, that's not necessarily the case. If it is closed and so finite, what's its topology? And there are many possible topologies for the universe. It can have a torus topology, a Möbius strip, many more complex topologies, and a lot of work has been done looking at what the spatial topology of the universe might be. Even more fascinating is the possibility that not only is this universe spatially closed, but it's closed up on a scale small enough that we have already seen right around the universe. We've seen everything that there is, and that's a testable possibility. If we lived in a small universe, that is one which closes up on itself on a scale smaller than the visual horizon, we could have seen our own galaxy as it was multiple times in the past. And I would really love it if that was the case. Unfortunately, it doesn't seem to be the case, but that is a possibility which you should be aware of. And then finally, do we need a multiverse? And some other people are going to talk about that in this series of lectures. The only point I'm going to make, it's not observationally provable because of horizons, which I'll mention in a moment. And some people even say there are billions of identical copies of you out there, and that simply is totally improbable. Now, the point about this is there are limits to data about the physical universe. This is the section of my talk. There are a variety of limits we can know about for a variety of reasons: the uniqueness of the universe, its vast size and scale, and the existence of horizon. Cosmology is unique about the sciences because there's only one universe. And by definition, there's only one universe. By definition, the universe is all that exists, or let me be more precise, all that exists that is connected to the bit of the universe that we can see. If there's completely disconnected universe, that's irrelevant because we can have no causal connection with them and know nothing about them. Now, we can't do experiments on the universe per se. We can't rerun the universe with the same or different starting conditions to see if things work out. Now, in most physics, you rerun many, many copies of the same thing and see what happens, and then you can get laws of what happens. We can't do experiments on the universe. It just is what it is. We're inside the universe, and we're not able to run experiments on the universe. Furthermore, we can't compare the universe with any similar objects, as we can in the case of mountains or stars or galaxies or elephants. In those cases, there are many similar things, and you can form statistics of those things by looking at a whole set of them. There's only one universe for us to observe. We can make many observations of that one universe, but they're all observations of the same single universe. And these are reasons why the universe of cosmology is different from all the other sciences. It's because the universe is unique. There isn't any other universe by definition, at least not one we can interact with. So it doesn't even make sense to talk about laws for the universe that some of my colleagues do. The very nature of a law is that it applies to multiple objects. All apples at the same place fall to Earth at the same rate. All planets move in elliptical orbits and so on. There's no other universe to which such a law can apply. And if there was a law, you could never prove that it was such a law, because you have to observe multiple examples of the thing to prove that they obey a law. So it doesn't make sense to talk about laws of the universe. So philosophy is important because of its unique nature. So testability is a key issue because we are talking about science. To what degree can you test cosmological models? There are major limits to what we can measure or observe. Because of the scale involved, we can't view the universe from a different point in space-time. So we conventionally talk about where we exist in the universe, our galaxy, as here, and the time and now. Now, in the case of the Earth, you can walk all around, you can travel all around the Earth. You can eventually see all the places in the universe. In the case of the Earth, you can eventually see all places on the Earth. You can view all of them from satellites traveling around. We can't view the universe from any other space-time point than the space-time point here and now. So we can only see the universe from one space-time point. I like to have the analogy of an ant trying to discover the nature of the Sahara Desert, and he climbs to the top of a sandhill, and all he can see is all that you can see from that one sandhill. He can't see the oceans, he can't see forests, he can't see anything else. All he can see is sandhills, and we're in the same position in the universe. All cosmological observations see objects as they were in the distant past. We can't see them as they are now, because light travels. We see them by light, which travels at the speed of light. We have to interpret them in the light of any evolution that may have taken place. And we can't see to earlier times than the last scattering surface, as the universe was opaque then. So there are particle horizons and visual horizons that limit the part of the universe we can see. By the way, event horizons are irrelevant to cosmology. So let me show you what I mean by showing you this. This is a conformal space diagram. This is our space. This is time and space. And I've I've enlarged the spatial scale to make the light cone at 45 degrees. And here, this is our past world line. This is the last scattering surface. This is the beginning of the universe. So this is our world line, and the matter, our world line starts at the Big Bang. Nuclear synthesis took place in the very early universe. Our world line crossed the last scattering surface, and here we are here. Now, we can't move off this because of the scale of the thing. We can't see the universe from any different position because if we travel for billions of years, we'd still be in our own galaxy. And we can't travel up and down here because this is 13 billion years. 50,000 years, we'll still be at the same space-time point. So we can only see the universe on one single past light cone. That hits the last scattering surface in a sphere, which is the last scattering surface. And that's what we see in those pictures I showed you. Now, the furthest matter we can see is limited by the visual horizon. Here's matter, which starts off in the Big Bang. This is its world line. We can't see it because our past world light cone runs into the last scattering surface, and light can't travel any further because it can't travel in this strongly scattering space. So this in this strongly scattering domain of the universe. So this matter is invisible to us. We simply can't see it. And this is one of the points about a multiverse. You can say anything you like about the multiverse, but it isn't visible because it's beyond the visual horizon. This is the visual horizon is the furthest matter that we can see. Furthermore, everything before the last scattering surface is invisible because the universe was opaque. So you can only see things which are this time of the last scattering surface. All of this is hidden. So you can't see the start of the universe. However, there's one point that you can see is that this is our past world line, and nuclear synthesis took place here, and stars formed elements here, which we can measure here and now. So we can do what we call geological kind of observations. If you look at elements here, they all originated somewhere our past light cone, and they give us information somewhere in our past light cone. So, this is a diagram showing you what we can and cannot have evidence about, and we can see the last scattering surface. I've shown you a picture of that. We can't see this galaxy or anything out there. You can't see anything earlier, but we can obtain some data about here through element abundances. Now, there's also what I call a physics horizon. There are limits to the energies we can reach in any particle experiments. Relevant physics in the early universe is untestable. This applies to the inflaton. The matter-antimatter symmetry in the universe depends on physics we can't test. Supersymmetry, supergravity aren't testable, or maybe this is now disproved, and we certainly can't test quantum gravity, string theory, M theory. We don't have colliders which can reach those energies, so there's what I call a physics horizon. Was there a start? And the answer is we don't know. We do not know if there was a start to the universe because that depends on quantum gravity, and we don't know if there was what kind of quantum gravity exists and if it predicts a beginning or not. Classically, we know the required energy conditions need not be true. So the famous singularity theorems depended on energy conditions, and inflation proves that those energy conditions were not true in the early universe. And in terms of quantum gravity, we don't know the relevant quantum theory of gravity. So we don't know if there was a start to the universe. I would guess that there was, but that's not a proof. And what we need to remember, some of my colleagues like to take that the universe was created out of nothing. But before the start of the universe, there was no space-time, there was no physics, and it's very difficult to talk about this. There was no before then. It's a contradiction in terms. So you can draw an arrow pointing to here, but nothing existed then because the whole concept of existence didn't exist then. The universe can't come into existence out of nothing because nothing did not exist, and it's quite difficult to talk about that, but it's very important, the idea that there was no before the beginning. Now, finally, I'm going to talk about some deep issues regarding the nature of the universe, issues that go beyond what science can say. Why does the universe exist? Why does it have the nature it does? Why are there laws of physics? Why are they what they are? And what kind of meaning is there in the universe? And the universe has non-physical aspects that are key to our existence and experience. They should be regarded as deep aspects of the nature of the cosmos. And the basic point, why does the universe exist? It's not a scientific question. Why does it have the nature it does? That, again, not a scientific question. Scientific explanation doesn't work before the universe exists. Again, I've explained that before the universe exists, space didn't exist, time didn't exist. And so none of these questions can be answered by scientifically. You can't do any experiments which tell you why the universe exists, why it has the nature it does, or why they're laws of physics, or why they are what they are. No scientific laws apply then. Metaphysical explanation is needed. That is explanation over and above that of physics and testable science. Science takes over only once the universe has come into existence with specific laws of physics governing its dynamics and with specific initial data. So I'm emphasizing that physics is strictly limited in what it can talk about and what it can explain. And it can't explain anything before the universe exists. And it can't explain why there are laws of physics, what their nature is, and so on. Now, there is one thing which is important. Life exists in the universe, and this is what's called the anthropic issue. The universe has a very special nature that allows life to exist, and that need not have been the case. As cosmologists, we can imagine many kinds of universe where life would not have been possible. If either some constant of physics, such as the ratio between the electromagnetic force and the strong nuclear force, or some relation to cosmology, such as the cosmological constant, had been significantly different, no planets at all would have existed. None of the evolutionary processes leading to life would have occurred. So some constants of physics have to be in a narrow range in order that life can exist, and some cosmological features have to be in a narrow range in order that life exists. Our universe is, in the sense, a fine-tuned universe. It has a very special nature. And Luke Barnes is going to talk about that, and it's going to be a very interesting talk. But why is this so? Why is the universe apparently fine-tuned for life? That is a philosophical question, which it's a very interesting philosophical question, but it's not a scientific question. It's a philosophical one. Now, this is what the laws of physics have to be special. And here is the value of the strong nuclear force, which holds nuclei together. Here's the value of electromagnetic force. These are on logarithmic scales. In this region, hydrogen can't form. In this region, chemical reactions are impossible. In this region, stars can't shine. In this region, carbon and heavy elements cannot exist. And carbon-based life is possible in this very small domain of here, of the relation between the strong nuclear force and the electromagnetic force. And so the question is, why did the universe exist in that very small domain? Now, of course, one answer is if it was out there, we wouldn't be here to see it. And so we wouldn't know anything. We wouldn't be asking this question because we wouldn't be here. But we want some other kind of answer if possible. Now, cosmology, if you plot the size of the universe against time, it could, in principle, expand very, very rapidly. It could expand very, very slowly. If it expands too slowly, then it depends on the ratio of kinetic energy to gravitational energy. And in this region here, the expansion is too slow. The universe collapses into a big crunch before life can form. In this part, the life expands very rapidly, and planets, galaxies and planets won't form. In this region, black holes will form, but and the big crunch will form before life can occur. Here, it's too rapid, and there simply won't be any planets or any galaxies because the universe expands too rapidly, and structure formation simply won't take place. If you have an exponential structure formation, there is no structure formation, and you have to be in this very narrow range where life is possible. And so this is the second kind of thing. So what we've got is we've got constraints on physics and we've got constraints on cosmology in order that life can form. Now, quite a number of people propose that the reason why this is true is because the multiverse exists. There are other explanations, but I'm not going to go into that because Luke Barnes is going to talk about that in detail. The outcome of cosmology today is that it enables us to exist. And I love this picture. This is an outcome of the nature of the universe. We exist and have this kind of existence because the universe has a very, very special nature which enables our existence. Now, the final thing I want to talk about is underlying everything that exists in the universe is what I call Platonic possibility spaces that underlie exists. And they are what I call the deep structure of the cosmos. Now, there's a whole series of possibility spaces, Platonic possibility spaces, and I'm going to just mathematics, physics, cosmology, biology, thoughts, behavior, and ethics. I'm only going to deal with the mathematics one and the ethics one, but there are possibility spaces for all of these things. For instance, physical possibility spaces depend on the structure of physics, and they're characterized by phase spaces. Cosmology's possibility spaces. I've written a book about phase spaces for cosmology. Biology possibility spaces depend on physics and so on. But anyhow, I'm only going to talk about mathematics and ethics. Now, what mathematics exists is determined by our explorations of eternal, unchanging mathematical possibility spaces. They hold everywhere in the universe at all times. Mathematics itself is not a social construct. It is our developing understanding of what is mathematically possible. And that's slightly confusing. I'll explain it in more depth in the next slide. Here's eternal, unchanging truth about the universe, Pythagoras' theorem. You have a triangle, a squared plus b squared is equal to c squared. And this is a very important one, which is true everywhere in the universe, the number pi. The ratio of the circumference to the diameter is pi, which is 3.14159, and so on, as you all know. Now, mathematicians didn't invent the number of pi, they discovered it. And they didn't invent Pythagoras' theorem, they discovered it. And what is very important is to distinguish mathematics itself, the abstract thing, and known mathematics, a social construct, because you'll find some people saying mathematics varies with time. We didn't know about the number pi, and then we didn't. We didn't know about Pythagoras' theorem, and we did. So known mathematics is indeed a social construct. It is what we know about the mathematics itself, the abstract thing. So what I'm claiming is that mathematics itself, mathematic truths are timeless, eternal. They were true at the start of the Big Bang. They're true on the Andromeda galaxy. They're true everywhere in the universe. They may even have been true before the beginning of the universe. What we know varies with time, and there is a projection of mathematics, pi mathematics, which depends on time, and this, what any particular culture or individual knows, changes with time, but the mathematics itself does not change with time, and that is a very important point to make, and that's what I've tried to explain. What mathematics exists is determined by our explorations of eternal, unchanging mathematic possibility spaces. And there's very deep discoveries taking place in mathematics at the moment about the deep structure of mathematics, and very deep stuff is going on. All of this holds everywhere in the universe at all times. And mathematics per se is not a social construct. It is our mathematics which we read about in textbooks, is our developing understanding of what is mathematically possible. And the same applies to physics. The laws of physics are the same everywhere in the universe as far as we're aware. Our knowledge of physics changes with time. So that's the first thing. The second thing, what socially exists is determined by our explorations of eternal, unchanging social and ethical possibility spaces. They are underlain by moral realism, the fact that some social structures and actions are either good or evil as a matter of fact, not as a matter of opinion. Now, this is where I am going way, way beyond physical cosmology. I'm going into an underlying structure which to me is very, very important. To me, it is very important that we should be able to say that if that some things which happen are evil as a matter of fact, not as a matter of opinion, that they can be stated to be evil as a matter of fact. That is the position of moral realism. Morality is real, and some things are good as a matter of fact, some things are evil as a matter of fact. And genocide, for example, is evil as a matter of fact. And what socially is done by our explorations of unchanging social and ethical possibility spaces. So I want to illustrate that now. This is some of the negative kinds of things that can happen. I'm not going to tell you where there is, but clearly something extremely bad is going on. Thousands of people have been killed. The people who did this do not care about human life. This is a completely contrasting thing, and I absolutely love this picture. This is a wonderful picture of a little guy looking with total trust and faith at someone who's doing the best he can for this little guy. And the contrast between these two pictures couldn't have been more dramatic. So it is crucial to be able to some action as evil as a matter of fact, not a matter of opinion. Examples of genocide, apartheid in my own country, and killing or torturing people for fun. This is the position of moral realism. Moral realism says that you can label those evil as a matter of fact, not of opinion. And I propose that moral realism is part of the deep, non-physical deep structure of the cosmos. It is true at all times and places, everywhere in the universe. The fact that things can be evil is the same on planets anywhere else in the universe. It does not depend on being on this particular planet. And again, exactly the same thing is true. You need to distinguish morality, what is good, the abstract thing, the thing which is an absolute fact at all times and places, and our ethical understanding. Different societies have different understandings, and they change over time. And part of the history of humanity is people changing their view about what good and what bad and what evil is. So it's exactly analogous to what happens in mathematics. Morality, what's good and what's evil, is the same at all times and places. There's a projection of an ethical projection. What any particular society or person understands varies with time, place, and society. It's in parallel with the difference between mathematical understanding, a social construct, and mathematical itself, unchanging Platonic reality, which is the same in the universe at all times and places. And this is my final thing I want to say. So how do you characterize this relation between good and evil? And what I propose is that there is a spectrum from coercion to kenosis, which takes values from -5 through 0 to +5. And I'm going to briefly explain that. -5, you're willing to indulge in genocide. You're willing to wipe out a population, wipe out every single member of that population, genocide, which has taken place in various cases. The one prime example being what happened in Germany during the Second World War. Level -4, you're not going to try to wipe out people, but you're willing to kill them and torture them in order to attain what you want. -3, you're willing to cause them physical harm, not going as far as killing them or torturing them, but you're very willing to cause them physical harm. -2, and So that's -5, that's -4, -3, -2. You're willing to undermine them, but not actually causing the physical harm. Indifferent, you don't care one way or the other. Here is what's called getting to yes. I'm willing to work with you to get something together for us. The golden rule, I will do for you what you would like to do for me. This is the role of forgiveness. I'm going to forgive you for what you've done, even though you caused me harm. This is Nelson Mandela and Desmond Tutu. And what is called kenosis is the idea that I am willing to suffer on your behalf, even if you are your enemy. And any ethical position can be placed somewhere on this scale, and you can determine where people are by how they behave, and it is empirically determinable. It's not just a matter of opinion. Right at this moment, there are people being killed in the Persian Gulf because certain people are willing to kill in order to gain what they want, and they do not care how many people they kill. It's empirically determinable that's the case. It was empirically determinable that the Nazi regime tried to wipe out the Jews as a whole. And so there's nothing, it's not a matter of opinion, it's a matter of determining what happened. The term forgiveness, you can determine that Desmond Tutu and Nelson Mandela ran the whole, they ran their whole political and moral campaign on the basis of forgiving people for what they had done. There was a Truth and Reconciliation Commission, which was based on this. So what I'm saying here is that the deep structure of the universe includes these kinds of things that I am now talking about. The universe is not restricted only to physical interactions. It includes the kinds of things which I've been talking about in this last section, the way people interact. They have to exist, so there has to be a possibility of existence. But once they exist, I'm saying that this scale, it can be applied to people, it can be applied to institutions, it can be applied to countries, and it can be applied to anywhere, anytime. And you can determine by empirically, and what I'm saying is anything to the at scales -4 or -3 is evil as a matter of fact, and anything to the right of 4 and 5 is good as a matter of fact. And so that's where I end.
Thank you very much, Professor Ellis. And this lecture, it is both scientifically rigorous and philosophically expansive. I am feel like what I want to say that most of the lectures what we go through we understand through our mind, but this lecture what I personally feel that it should be feel. So thank you so much for this deep discussion, and the big picture is actually bigger than for us to perceive, and you so nicely described the fundamental issues of cosmology. It's a classical presentation, sir. Now we'll go towards the question and answer session. So again, a gentle reminder to the audience. Please take the question through the QR code displayed here on the screen, and you can use also the Google form link that is being shared in the chat box. We now open the floor for the final discussion of the day. Okay, so the first question from Professor Tejinder Singh, Tata Institute of Fundamental Research. It is said that inflation predicts multiverses, each with its own laws. The enormous landscape of string theory, vacua, is invoked as supporting evidence for inflation and multiverses. Do you agree with this? Or is this telling us that inflation and string theory are incorrect descriptions of physical reality.
Hi, Chajendra. Nice to hear from you. Yeah, there are many versions of inflation do predict multiverses. Now, that is true, but the first problem comes, but there's over 200 versions of inflation, and not all of them predict multiverses. But nevertheless, some of them do. Now, one of the points is spatial homogeneity. If the universe is spatially closed, then that doesn't necessarily work. But the deeper point is the landscape of string theory vacua is invoked. Now, there is no evidence whatever that string theory is true. And in fact, it requires supersymmetry. And as far as I can tell, there's evidence against supersymmetry at the present time. So, but the difficult point is, supposing we believe in string theory, suppose supersymmetry is true. The question is, how do you get different physics in the different multiverse domains? And I know that there is a mechanism that I think it's the KKLT mechanism, which I'm not an expert, but that seemed to me a very, very a dubious thing. But I want to make one point about this, is that that claim that you get the multiverse, it depends on which of the models is correct, which potential is correct. And supposing that that you have one which creates a multiverse. Now, you have to have a multiverse which allows life to exist in at least some of its universe domains. And what you've done from a philosophical viewpoint, you haven't solved the anthropic issue. You've just lifted it one level up, because the question then is, well, why is my multiverse one that admits life to exist? I can create for you a multiverse which does not allow life to exist. So it is a possible solution if you believe in string theory, and if you believe in a KKLT mechanism or something similar, which is a lot of very big ifs, particularly given that supersymmetry doesn't seem to be true. But the further issue then is why does that particular potential hold in your multiverse?
Okay, thank you, sir. Proceeding to next question. Wonderful lecture. Really provided a big picture. You mentioned about spaces of thoughts. Could you elaborate on it?
Yeah, there's a wonderful book talking about this. It's called the Library of Babel by John Louis Borges. Is that you need to start thinking about thoughts, and what you can do. The Library of Babel is a wonderful novel by a guy called Borges, and he envisages a library, a huge library, which contains all possible books that can be written in the universe. So you can say, hang on, wait a minute, there's an infinite number of books, but there aren't. And the reason is the following. It's a very interesting reason. If I start talking to you, my sentence must have a finite length. And the reason is because you must remember the beginning of the sentence by the time you reach the end. Now, what that means is that a sentence must be, we have limits in short-term memory, and that limit is 7. And there's a famous paper called The Magic Number 7 pi to minus 2. If a sentence is more than 7 times 7, 7 slots, each with 7 words, you can't remember it. By the time you reach the end of the sentence, you can't remember the one that began. So in other words, any possible sentence which conveys a coherent thought has a maximum length, and I'll be quite generous. Let's say it's 490 words. Okay. Well, what that library is, the Library of Borg, is it's a library that contains all possible books with all possible thoughts and in all possible languages. It's actually really worth reading that book. And the Library of Babel contains all possible thoughts. And those thoughts contain thoughts. Most of the books in the Library of Babel are complete nonsense, but they contain all possible books that are not nonsense and all possible books that are slightly different from the ones that have been written. And the key point about this is that this is a finite number. It's a finite space. It's not an infinite space. As soon as you start the word infinite, then things get difficult. But the number of possible thoughts is finite. It's a very, very large number. It's a huge number. But nevertheless, what I claim is one of the possibility spaces is a space of all possible thoughts, and that is a finite space, and that again has been the same since the beginning of time. Now, once you start looking at this, you realize there's a similar space, a space of all possible images. And we're seeing that nowadays because any picture, such as a standard digital picture, has got a finite size. It's quite a large size. It's I can't remember how many bits it is, but any picture. And so you can have a space of all possible images because it's a finite space. And it's the same for music. You can have a space of all possible tunes and all possible songs. Each of these have finite possibilities. So underlying what actually exists, there's a space of possible books which contains all possible thoughts. There's a space of all possible images and a space of all possible music.
Okay, thank you, sir. Moving to the next question. Okay, so this is from Inyavan. Modern cosmology explains the evolution of the universe through well-tested physical laws such as general relativity. Yet the large-scale structure of the universe still depends strongly on its initial conditions. From a fundamental perspective, do you think the initial conditions of the universe be regarded as something that requires a deeper physical explanation, or might they simply be bureaucratic facts about our universe?
That's a very good question, a very nice question. Now, you run into the problem I talked about, the uniqueness of the universe. You can make any theory about initial conditions you like, but you can't test it because there's only one universe. So you can't run different universes and test them. You can't observe universes. So make any such theory you like, and you can't test it. So in that sense, you can make such a theory, but it's simply non-scientific. So now, Roger Penrose has tried to do such a theory with his conformal condition at the Big Bang, and it's very well motivated. And Stephen Hawking has had a very interesting thing with his no boundary conditions. Now, just to comment on each of these, Roger Penrose then goes into his conformal cyclic cosmology, and I just don't happen to think that's a good way, as a way of trying to explain that initial condition, and I don't think that works for reasons I could explain. And Stephen Hawking's one depends on the idea of a wave function of the universe, and I don't happen to believe there is such a thing as the wave function of the universe. There's a whole theory of quantum cosmology which depends on the concept of the existence of the wave function of the universe. Before you have a theory of the wave function of the universe, firstly, it depends on the Wheeler-DeWitt equation, which is an ill-defined equation which has not been tested and cannot be tested. And secondly, I simply don't believe that there is a wave function of the universe, and I could go into that. I've written a paper about this. The idea of a wave function of the universe is that there is one single universe which covers the whole universe. Now, the problem with this is that a wave function evolves linearly. The Schrödinger equation is linear, the Dirac equation is linear, Feynman's path integral is a linear structure. And I could explain all of that. And so my resolution of this is to say all of these ideas are mistaken because there does not exist a single wave function for the entire universe. What does exist is local wave functions. And the entire universe is covered with local wave functions, each of which locally obeys the Dirac equation or Schrödinger equation. And this is in complete analogy with general relativity, when the key to solving the large-scale structure of space-time was to understand that in general, you cannot use a single coordinate system to cover the whole of space-time. You need an atlas of many, many coordinate systems in order to discover space-time. And I believe exactly the same is true for quantum physics. You need an atlas of local wave functions, not a local wave function, and that immediately solves a great many problems about cosmology.
So we have a series of questions with us. So would you please allow us to take a couple of more questions? So can I proceed with a couple of more questions if you allow?
I think I should like to stop now. I've been going for an hour.
Okay. Okay. Thank you so much, sir. Thank you for this these questions and answer session. And I would like to once again express our sincere gratitude to you, sir, on behalf of the Bhaktivedanta Institute and all the audience. Thank you, sir.
Thank you so much.
So I'd like to come for the tomorrow's sessions, and today we have very interesting discussion in different topics. So tomorrow we have another line of world-renowned speakers. At 5 p.m., Professor Louis Marmot, York University, Toronto, Canada, and he'll be speaking on an optical illusion at crossroads of cosmological models. At 6 p.m., Professor Mario Livio, he'll be speaking on space telescope science. He's from Space Telescope Science Institute, USA, and his topic is Earth Exceptional? And at 7 p.m., Professor Tejinder Pal Singh, ex-professor, Tata Institute of Fundamental Research, Mumbai, and a visiting professor, IUCAA, he'll be speaking on quantum theory, gravity, and the cosmos. So here we have a screen that shows the mathematics Samvigyanam volume 11, the mathematics of universal beauty. Unlock the mathematical elegance of the universe in Samvigyanam volume 11. The renowned astrophysicist Professor Mario Livio guides readers through the golden ratio, revealing how this divine proportion dictates the structure of galaxies and the very fabric of reality. It is an essential read for those seeking to bridge the gap between science and symmetry. We also have another series of Samvigyanam Volume 10, the Astrobiology of Our Origins, delve into the profound mysteries of the deep cosmos with Volume 10 of Samvigyanam. This edition features a centerpiece article by the world-renowned astrobiologist Professor Chandra Wickramasinghe, explore his groundbreaking research on cometary panspermia, challenging our fundamental understanding of how life began on Earth and its ancient ancestral connection to the stars. So the timing, I'll again repeat, it is from Monday to Friday. It is from 5 p.m. to 8 p.m. IST, and Saturday and Sunday it is in 10 a.m. and to 1 p.m. IST, as per the Indian Standard Time. So as we conclude day 3, so what we have witnessed today is not merely a sequence of lectures, but a subtle shift in perspective. We begin with a question about dark energy, something we cannot see yet infer. We move through a framework that challenges cosmological orthodoxy. And we concluded a reflection on whether a complete picture of the universe is even attainable. If there is one thread connecting today, it is this: the universe is not only expanding, so is the space of our uncertainty. So, on behalf of the Bhaktivedanta Institute, I extend our deepest gratitude to our speakers and participants across the globe. Your presence makes this not just a lecture series, but a shared intellectual journey. We met today not because the universe is understood, but because it is not. Therefore, we look forward to continuing this voyage tomorrow. Until then, stay curious, stay critical, and remain open to being surprised by the universe. Thank you and have a good day or evening wherever you are in the world.